There is a world sitting between Mars and Jupiter that should not exist. It is nearly 600 miles across. It contains more fresh water than all the rivers, lakes, and streams on Earth combined. Its surface is scarred by ancient impacts and dusted with salt deposits, so bright they once fooled astronomers into thinking they were seeing city lights. And for more than 2 centuries, nobody could agree on what it was. Planet, asteroid, dwarf planet, something else entirely. Every time scientists thought they had the answer, Ceres changed the question. On the first night of the 19th century, a quiet Italian astronomer pointed his telescope at a patch of sky between Mars and Jupiter and found a faint point of light that was not supposed to be there. He tracked it for weeks, watching it drift against the background stars with the slow deliberation of something in orbit, and he did what any astronomer of his era would do. He called it a planet. For nearly 50 years, textbooks listed it alongside Mercury, Venus, Earth, Mars, Jupiter, and Saturn. School children across Europe memorized its name. Maps of the solar system printed in London, Paris, and Berlin included it as a full member of our cosmic neighborhood. Professors lectured about it. Charts were updated. The solar system finally was complete. Then, one by one, other objects began appearing in the same region of space: Pallas, Juno, Vesta. Small, faint, and orbiting far too close to each other to be separate planets. And everything changed. Ceres was stripped of its title, demoted to a mere asteroid, reclassified as debris. And then, for the better part of 200 years, forgotten. But forgetting Ceres was a mistake, because Ceres was never what it seemed. What most people picture when they hear the word asteroid is a dead, grey, potato-shaped chunk of rock tumbling through the void. Something inert. Something ancient, something with nothing left to say. And for decades, even centuries, that was exactly how the scientific community treated Ceres. It was catalogued, measured, filed away, and ignored in favour of larger, flashier objects. Mars with its canyons and rust-coloured dust storms, Jupiter with its swirling great red spot, and moons the size of planets, Saturn with its luminous rings. Even Pluto, tiny frozen Pluto, orbiting at the ragged edge of the solar system, received more public attention, more spacecraft proposals, and more pop culture affection than Ceres ever did. The asteroid belt was treated as a cosmic parking lot, a dull stretch of emptiness you pass through on your way to somewhere more important. And Ceres, despite being the largest object in the belt by a wide margin, despite containing roughly a third of the belt's total mass, was just the biggest piece of rubble in a field of rubble. Or so everyone assumed. Then, in 2015, a spacecraft called Dawn arrived at Ceres after a journey of nearly 8 years and 3.5 billion miles. It had travelled farther than any ion-propelled spacecraft in history. It had already orbited one world, the asteroid Vesta, and left it behind to reach this one. And what Dawn found at Ceres shattered every assumption that 2 centuries of astronomical consensus had built. Bright white spots glowed from the floor of an ancient impact crater, looking for all the world like something reflective, something fresh, something that had no business being on a body that was supposed to have been dead since before complex life appeared on Earth. A lone mountain rose from the surface, steep-sided and symmetrical, taller than any peak in the Appalachians, standing in solitary defiance of every geological model that said it should not be there. The chemistry of the surface revealed organic molecules, the very building blocks of biology, concentrated in specific regions as though they had been placed there with intention rather than scattered by chance. And beneath the icy crust, hidden from direct observation but betrayed by subtle variations in Ceres's gravitational field, scientists found evidence of something that rewrote the rules: liquid water, a subsurface ocean. On a world smaller than the state of Texas, colder than the Antarctic plateau, orbiting in the frigid darkness 3 times farther from the sun than Earth. Here is what most people never hear. In 2006, the same year Pluto was famously stripped of its planetary status in a decision that generated global outrage and inspired bumper stickers and protest rallies, Ceres was quietly promoted. It was reclassified from asteroid to dwarf planet, placed in the same category as Pluto itself. But while Pluto's demotion became a cultural flashpoint, a punchline on late-night television, and the subject of passionate debate in classrooms around the world, Ceres received almost no attention at all. The most mysterious world in the inner solar system was given a crown, and nobody noticed, nobody cared. And that, in retrospect, may be one of the greatest oversights in the history of modern astronomy. Because Ceres is not just a reclassified rock. Ceres is not just a slightly larger than usual asteroid with a new title. Ceres might be one of the most important objects in the entire solar system for understanding where life can exist. Not where we expected it, not where we have been pointing our telescopes and sending our rovers, but in the cold, dark, overlooked places we dismissed for centuries as wastelands unworthy of investigation. By the end of tonight, you are going to understand why Ceres matters far more than its small size suggests. You are going to understand how a world barely larger than a medium-sized country could reshape our understanding of habitability in the solar system. You are going to follow the scientists who refused to accept easy answers, who fought for funding to send a spacecraft on an 8-year journey to visit an object most people have never heard of, and who found something so unexpected that it forced the entire field of planetary science to rethink its most fundamental assumptions about what makes a world alive and what makes it dead. And you are going to confront a possibility that is as thrilling as it is unsettling. That the universe may be full of hidden oceans, full of worlds that look lifeless from the outside, but harbour secrets beneath their surfaces. And that the question of whether life exists beyond Earth may not be answered on Mars or Europa or Titan, but on a tiny overlooked dwarf planet that humanity spent 2 centuries throwing away. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand Ceres, you first have to understand the gap. For centuries, astronomers stared at the solar system and noticed something that did not add up. Between Mars and Jupiter, there was a void, an enormous, conspicuous stretch of empty space where the mathematical patterns governing planetary orbits said a planet should exist. And the absence of that planet nagged at the scientific mind like an unanswered question written on a chalkboard in a room nobody was allowed to erase. This was not a vague suspicion or a poetic intuition. It was a precise mathematical prediction. In 1766, a Prussian astronomer named Johann Daniel Titius noticed a curious numerical pattern hiding inside the distances of the known planets from the Sun. If you took a simple sequence of numbers 0, 3, 6, 12, 24, 48, 96, where each number after 3 was double the previous one, and you added 4 to each, and then divided by 10, the resulting sequence matched the actual distances of the planets from the Sun with eerie precision. Mercury sat at roughly 0.4 astronomical units from the Sun, Venus at 0.7, Earth at 1, Mars at 1.6, Jupiter at 5.2, Saturn at 9.5. Each distance fit the pattern, but there was a gap. The sequence predicted a planet at 2.8 astronomical units, right between Mars and Jupiter, and nothing was there. The pattern was popularized by another astronomer, Johann Elert Bode, and became known as the Titius-Bode law. For years it was treated as a curiosity, a mathematical coincidence with no deeper significance. Then in 1781, William Herschel discovered Uranus, and its orbital distance, 19.2 astronomical units, matched the Titius-Bode prediction almost perfectly. The astronomical community was electrified. If the law had correctly predicted Uranus, a planet nobody even knew existed, then surely the gap at 2.8 astronomical units was real. Something was hiding between Mars and Jupiter. It needed to be found. In the final years of the 1800s, a Hungarian astronomer named Franz Xaver von Zach organized an unprecedented international collaboration to search for the missing planet. He recruited 24 of the finest observational astronomers in Europe and formed a group that became known, somewhat grandly, as the Celestial Police. The name was not entirely a joke. They viewed themselves as enforcers of cosmic order, tasked with apprehending a fugitive planet that had eluded detection for too long. Each member was assigned a specific zone of the zodiac to patrol systematically, scanning the sky with telescopes, recording every faint point of light, and checking for anything that moved. It was the first coordinated astronomical search campaign in history, a remarkable exercise in scientific cooperation at a time when communication between countries relied on hand-delivered letters. And it failed. The man who found the missing planet was not a member of the Celestial Police. He was not even looking for it. Giuseppe Piazzi was an Italian Theatine monk, a mathematician, and the director of the Palermo Astronomical Observatory in Sicily. On the first night of January in 1801, the first night of the new century, Piazzi was engaged in work that was vital but deeply unglamorous. He was compiling a star catalogue. This meant spending night after night, year after year, measuring the precise positions of thousands of stars through his telescope, recording their coordinates with painstaking care, and comparing them against existing catalogues to correct errors and fill in gaps. Star catalogues were essential tools for navigation and astronomy, but creating them was grueling, eye-straining labour that most astronomers considered beneath their ambitions. Piazzi did not share that attitude. He believed that careful observation was the foundation of all science, and on that New Year's night, in the cold clarity of the Sicilian sky, his devotion to precision changed the history of astronomy. He noticed a faint point of light in the constellation Taurus that did not appear in any existing catalogue. It was dim, unremarkable, easily overlooked. He marked its position and planned to confirm it the following night. When he returned to his telescope 24 hours later, the point of light had moved. The shift was tiny, just a fraction of a degree against the background stars. But it was unmistakable. Stars do not move from night to night. Comets move, but they typically show a fuzzy halo, a coma, and a tail. This object had neither. It was sharp, point-like, clean. It moved like a planet. Piazzi tracked the object for 41 consecutive nights, recording its position each time with the extraordinary care that was his hallmark. The path it traced through the sky was not the rapid arc of a nearby comet, but the stately drift of an object orbiting far from the Sun. His calculations placed it between Mars and Jupiter, right where the Titius-Bode law predicted a planet should be. But Piazzi was cautious. He did not rush to announce the discovery of a new planet. Instead, he wrote private letters to two colleagues, Bode in Berlin and Barnaba Oriani in Milan, describing his observations and sharing his data. Then illness intervened. Piazzi fell sick, and by the time he recovered, the object had moved too close to the Sun in the sky to observe. It was lost. The missing planet had been glimpsed for 41 nights and then swallowed by the glare of daylight. This created a genuine scientific crisis. Without enough observations to compute a reliable orbit, no one could predict where the object would reappear when it emerged from behind the Sun. It could be anywhere along a vast arc of sky. Searching for it without an orbital prediction would be like searching for a specific grain of sand on a beach. Enter Carl Friedrich Gauss. In 1801, Gauss was a 24-year-old mathematician already recognized as one of the most gifted minds in Europe. He had published his first major work, the Disquisitiones Arithmeticae, that same year, a book that would become one of the foundational texts of modern number theory. When Gauss learned of Piazzi's predicament, the lost object between Mars and Jupiter, he saw it not as an astronomical problem, but as a mathematical one, and mathematical problems were his native territory. Using only Piazzi's 41 observations, Gauss developed an entirely new method for computing the orbit of a celestial body from a minimal number of position measurements. The method was brilliant, efficient, and unprecedented. It would later form the basis of modern orbital mechanics and is still used by astronomers today, more than 2 centuries after Gauss first worked it out on paper by candlelight. His calculations produced a prediction. The object would reappear in a specific part of the sky on a specific date. On the last night of December in 1801, nearly a full year after Piazzi's initial discovery, the astronomer Heinrich Olbers pointed his telescope at the coordinates Gauss had predicted. There, exactly where the mathematics said it would be, was the faint point of light. Recovered, found again. Gauss had pulled an invisible world out of the sky using nothing but numbers. Piazzi named his discovery Ceres Ferdinandia, honouring both the Roman goddess of agriculture, the patron deity of Sicily, and King Ferdinand of Naples, his royal patron. The royal name was eventually dropped and the object became simply Ceres. Piazzi called it a planet, Bode called it a planet, the astronomical world agreed, the gap was filled. The Titius-Bode law was triumphant. The solar system, with its new eighth member, made elegant sense for exactly 1 year. In March of 1802, Heinrich Olbers, the same astronomer who had recovered Ceres using Gauss's calculations, discovered a second object orbiting in the same region of space. He named it Pallas. It was roughly similar in brightness to Ceres, suggesting a comparable size. The discovery was troubling. Two planets sharing essentially the same orbital zone was difficult to explain. No existing theory of planetary formation predicted such a thing, but the astronomical community absorbed the surprise and moved on. Pallas was added to the list of planets. The solar system now had 9 members. 2 years later, in 1804, Carl Ludwig Harding found a third object in the same zone. He called it Juno. In 1807, Olbers found a fourth Vesta. 4 objects, all orbiting between Mars and Jupiter, all too faint to show any visible disk through even the finest telescopes on Earth, all far smaller than any previously known planet. The clean, orderly picture of the solar system, 1 substantial planet per orbit, each a dignified and solitary world, was crumbling into chaos. William Herschel, the most famous astronomer of his age, the discoverer of Uranus, and cataloguer of thousands of nebulae and double stars, looked at the growing mess between Mars and Jupiter and proposed a radical solution. These objects were not planets, he argued. They belonged to an entirely new category. He coined the word asteroid, from the Greek asteroides, meaning star-like, because through a telescope they appeared as points of light indistinguishable from stars, rather than as tiny disks like proper planets. The term was met with resistance. Some astronomers defended the planetary status of Ceres and its companions. The debate simmered for decades, growing more heated as the number of known objects in the zone continued to climb. By 1850, more than 10 had been found. By 1900, over 400. The case for calling them planets had long since collapsed. By the middle of the 19th century, Ceres had been firmly reclassified as an asteroid, not a planet. Not even a special kind of asteroid, just the largest chunk of rock in a belt of debris. And with that reclassification came a profound loss of scientific attention. Once Ceres was filed under asteroid, it became invisible. The great telescopes of the 20th century pointed at galaxies and quasars, and the cosmic microwave background. The great space missions went to the Moon, to Mars, to Venus, to the outer planets and their spectacular moons. Nobody wanted to spend hundreds of millions of dollars sending a spacecraft to visit a rock. That neglect rested on a fundamental misunderstanding of what the asteroid belt actually is. Popular culture, shaped by decades of science fiction films and television shows, depicts the belt as a dense, chaotic, dangerous field of tumbling boulders. Spaceships dodge and weave. Rocks collide in showers of debris. The belt is portrayed as an obstacle course, a gauntlet, a demolition derby. That image is wrong. It is not just slightly wrong. It is spectacularly, almost ludicrously wrong. The asteroid belt is mostly empty space. The total mass of every object in the belt combined, every boulder, every pebble, every grain of dust, is less than 4% of the mass of the Moon. If you gathered it all together, it would form a body smaller than Ceres itself. The average distance between objects larger than 1 kilometer in the belt is roughly 1.9 million miles. If you could stand on Ceres and look out in any direction, you would see nothing. No tumbling rocks, no chaotic debris field, just the vast, silent, star-filled blackness of interplanetary space, stretching to the horizon and beyond, indistinguishable from the emptiness between any other 2 planets. Spacecraft that have passed through the belt, including Pioneer 10, Pioneer 11, Voyager 1 and Voyager 2, did so without even noticing. No evasive maneuvers were required. No rocks needed dodging. The belt, despite its fearsome reputation, is one of the emptiest regions of the solar system, and yet Ceres dominates this emptiness. It is the undisputed sovereign of the asteroid belt, the gravitational anchor of a realm that stretches hundreds of millions of miles. Ceres contains roughly 1/3 of the total mass of the entire belt. Think about that for a moment. Imagine gathering every single object in the asteroid belt. the millions of rocks and boulders and dust grains scattered across a region of space wider than the distance from Earth to Mars, and placing them all on a cosmic scale. Ceres alone would account for about 32% of the total weight. It is not first among equals, it is the giant among pebbles. To grasp its physical scale, consider that Ceres is approximately 587 miles in diameter. That is roughly the distance from London to Edinburgh, or from Los Angeles to Salt Lake City. If you could drive across it at highway speed, the trip would take about 9 hours. Its surface area is approximately 1,100,000 square miles, roughly the same as the total land area of India. If Ceres were placed on top of the United States, it would cover the state of Texas with room to spare in every direction. It is large enough that its own gravity has pulled it into a nearly perfect sphere, an oblate spheroid, slightly flattened at the poles, a shape that distinguishes it fundamentally from the irregularly lumpy asteroids that share its neighborhood. Vesta looks like a battered potato, Eros looks like a bent peanut, Ida looks like a misshapen shoe, Ceres looks like a world, because that is what it is. And there is one more thing that sets Ceres apart from everything else in the asteroid belts, something that was not fully appreciated until the Dawn mission revealed its significance. Water. Ceres is rich in water, not the kind of water that exists as fleeting traces of moisture clinging to mineral grains. The way water has been detected on the surfaces of some asteroids, and even on the Moon. Ceres is estimated to contain between 100 and 200 million cubic kilometers of water, mostly in the form of ice mixed with rock in its thick mantle. To put that in perspective, the total volume of fresh water in all of Earth's rivers, lakes, and glaciers is roughly 35 million cubic kilometers. Ceres holds several times more than that. If the ice in Ceres' mantle were somehow melted and poured onto the surface of Earth, it would create a global ocean tens of meters deep. For most of the 20th century, none of this mattered. Ceres was classified as an asteroid, and asteroids were boring. The scientific consensus was clear and unquestioned. Ceres was a ball of rock and ice, frozen solid, geologically dead, scientifically uninteresting. It was too small to have retained internal heat, too far from the sun to have liquid water, too irrelevant to justify the cost of a spacecraft visit. It was, in the eyes of the planetary science community, a perfectly preserved fossil of the early solar system, interesting only in the way that a museum exhibit is interesting, something to look at, catalogue, and leave behind. That consensus held for decades. It held through the Apollo era, through the Voyager missions, through the golden age of Mars exploration. Nobody questioned it. Nobody had reason to, but hints had appeared. In the early 2000s, before Dawn had even launched, observations from the Hubble Space Telescope and the Keck Observatory in Hawaii offered tantalizing clues that Ceres might not be as dead as assumed. In 2005, astronomers using Hubble's high-resolution camera captured the best images of Ceres ever taken from Earth orbit. Even at a distance of more than 170 million miles, the images revealed a surface that was not uniform. There were bright patches and dark patches. There was a suggestion of a large flat basin in one hemisphere and a brighter region that some researchers tentatively linked to a possible impact crater filled with fresh ice. The images were blurry, ambiguous, and frustratingly inconclusive, but they were enough to make a handful of planetary scientists argue that Ceres deserved a closer look. Separately, thermal models developed in the 2000s by researchers including Thomas McCord and Christoph Sotin had begun to suggest that Ceres might have undergone more complex geological evolution than previously assumed. These models, based on the latest estimates of Ceres' composition and the abundance of radioactive elements in primitive solar system material, indicated that Ceres had almost certainly been warm enough in its early history to differentiate into layers. A dense rocky core surrounded by a thick mantle of ice and hydrated minerals. Some versions of the models even suggested that a liquid water ocean might have existed beneath the surface for 1 billion years or more before eventually freezing. The idea that Ceres had once been an ocean world, even briefly, was enough to justify a mission. What nobody expected was that the ocean might still be there, and then NASA built a spacecraft called Dawn, and everything we thought we knew fell apart. Dawn was one of the most ambitious robotic exploration missions ever attempted. It was designed to do something no spacecraft had ever done before: orbit two separate bodies in the asteroid belt using a single vehicle. The engineering challenges were formidable. Conventional chemical rockets burn their fuel in minutes, producing enormous thrust, but leaving the spacecraft coasting for the rest of its journey on whatever momentum the burn provided. To orbit one body, fire the engines again, leave orbit, travel to a second body, and enter orbit there, you need far more fuel than any chemical rocket can carry. The mission was impossible with conventional propulsion. The solution was an ion drive. Ion propulsion had been theorized since the 1960s, but had never been used as the primary engine for a deep space mission of this scale. The principle is simple. An ion drive takes atoms of xenon gas, strips away one of their electrons to create positively charged ions, and then accelerates those ions through an electric field to speeds of roughly 90,000 miles per hour. The accelerated ions are expelled from the back of the spacecraft, and by Newton's third law, the spacecraft is pushed in the opposite direction. The thrust produced is absurdly small. At maximum power, Dawn's ion drive generated about 90 millinewtons of force, which is roughly equivalent to the weight of a single sheet of paper resting on the palm of your hand. If you held your hand behind the exhaust nozzle, you would feel nothing. You might question whether the engine was even on. But here is where the beauty of ion propulsion reveals itself. A chemical rocket burns for minutes. An ion drive can burn for years. That tiny, imperceptible push, applied continuously for months and years on end, accumulates into an extraordinary change in velocity. Dawn's ion engine operated for a cumulative total of more than 5.9 years of thrust time over the course of its 11-year mission. By the end, it had changed its velocity by more than 25,000 miles per hour, a figure that would be impressive for a chemical rocket and is remarkable for an engine that cannot push a piece of paper off a table. Dawn launched from Cape Canaveral in September of 2007. It used a gravitational slingshot past Mars in February of 2009 to pick up speed and adjust its trajectory. It arrived at Vesta, the second largest object in the asteroid belt, in July of 2011. It spent 14 months orbiting Vesta, mapping its surface in extraordinary detail, measuring its gravity field, and analyzing its mineral composition with spectrometers. What Dawn found at Vesta confirmed that it was a dry, rocky protoplanet differentiated into a metallic core, a rocky mantle, and a basaltic crust, heavily cratered and scarred by a colossal impact at its south pole that had blasted material all the way into interplanetary space. Some of that material eventually fell to Earth as meteorites, a special class called howardites, eucrits, and diogenites, which scientists had been studying in laboratories for decades without knowing they came from Vesta. Then Dawn fired its ion drive once more and left Vesta behind, spiraling slowly outward toward its final destination. The journey from Vesta to Ceres took 2.5 years, a long and lonely cruise through the emptiness of the asteroid belt. During the transit, the Dawn team refined their plans for Ceres observations, debated what they might find, and ran simulations of every conceivable scenario. They expected a cratered, dusty, frozen surface, probably similar to Vesta, but with a higher proportion of water ice mixed into the regolith. They expected geological monotony. They expected to confirm the textbooks. What they got instead was a mystery that would consume the careers of dozens of scientists for the next decade. On March 6, 2015, Dawn slipped into orbit around Ceres, captured by the dwarf planet's modest but sufficient gravity. It was moving slowly, creeping into orbit with the gentle deceleration of its ion drive, a balletic contrast to the violent braking burns of chemical-propelled spacecraft. Dawn became the first spacecraft in history to orbit a dwarf planet. It had also become the first spacecraft to orbit 2 extraterrestrial bodies, a feat made possible only by the extraordinary efficiency of ion propulsion. It had traveled more than 3.5 billion cumulative miles since launch. It had orbited 2 separate worlds, and it was about to discover that the second world was nothing like anyone expected. The first images came from a distance of more than 29,000 miles. They were grainy, pixelated, barely more than smudges of light and shadow, but even in those early frames, something was wrong. Inside a large impact crater near the equator, two intensely bright patches shone against the dark surface like headlights in fog. The contrast was jarring. Ceres' average surface reflects about 9% of the sunlight hitting it, roughly as reflective as freshly poured asphalt on a new highway. The bright spots reflected more than 50%. They blazed against the dark terrain like beacons, impossible to ignore, impossible to explain with any existing model of asteroid surface composition. Nothing in the Dawn team's predictions had prepared them for this. The images went viral. Social media erupted with speculation: alien cities, ice geysers, reflective mineral deposits, secret underground bases. The theories ranged from the plausible to the absurd, but the underlying sentiment was universal. This was not supposed to be there. As Dawn spiraled closer over the following months, lowering its orbit in carefully planned stages to increase the resolution of its instruments, the bright spots resolved into a complex of reflective deposits scattered across the floor of a crater named Ocata. The crater itself was about 60 miles wide and roughly 34 million years old, formed by the impact of a sizable asteroid or comet. The deposits were concentrated in two areas: a central dome called Cerealia Facula, roughly 9 miles across and rising several hundred feet above the crater floor, and a more diffuse bright region to the east called Venalia Faculae. The spectral analysis revealed their composition: sodium carbonate, a salt, the same mineral found in soda ash, in laundry detergent, in the chalky white deposits left behind when saltwater evaporates in a desert basin. Sodium carbonate does not form in a vacuum. It does not condense from sunlight or precipitate from cosmic radiation. On Ceres, its presence carried an unmistakable message. Salty liquid water had risen from somewhere beneath the surface, percolated through cracks in the crust, and reached the floor of Ocata crater. There, exposed to the vacuum of space, the water sublimated away, and the dissolved minerals were left behind as a bright, crystalline residue. The process is called cryovolcanism, and the timing was devastating to the old models. The deposits were fresh. Spectral analysis suggested some of the material could be as young as a few million years, possibly much younger. On a world that should have been geologically dead for 3 billion years, this was like finding a pulse in a patient who had been in the morgue for a week. The second revelation was Ahuna Mons, a mountain standing roughly 3 miles tall and 11 miles across at the base, rising from an otherwise featureless plain in the southern hemisphere. Its sides were steep. Its summit was flat. It stood entirely alone, with no mountain range, no volcanic chain, no tectonic ridge around it for context. There was nothing else like it anywhere on the surface. It looked like a dome, or a blister, or a monument built by geological forces that had no business operating on this world at this point in its history. Further analysis suggested it was a cryovolcanic construct, built from the inside out by icy material welling up from the interior and piling onto the surface. There is another way to appreciate the strangeness of Ahuna Mons. On Earth, mountains form through well-understood geological processes. The Himalayas were pushed up by the collision of tectonic plates over tens of millions of years. The volcanic peaks of the Cascades and the Andes were built by magma, rising from subduction zones where one plate slides beneath another. Even the shield volcanoes of Hawaii, which rise from the middle of a tectonic plate, are explained by a persistent hotspot in the mantle that feeds magma to the surface over millions of years. Every mountain on Earth has a mechanism, a source of energy, a geological engine driving its formation. Ahuna Mons has none that fit the textbooks. It stands on a world with no tectonic plates, no subduction zones, no mantle plumes, and, theoretically, no internal heat source powerful enough to push material through miles of frozen crust. It exists as an accusation against our models, a physical monument to something we do not understand. And there was a fourth discovery, one less visually dramatic but scientifically profound. Dawn's gamma-ray and neutron detector mapped the distribution of hydrogen beneath Ceres' surface. Hydrogen is a proxy for water, because water molecules contain hydrogen atoms that interact with cosmic rays in detectable ways. The data showed that Ceres' subsurface is rich in water ice, especially at higher latitudes, where the ice lies just beneath the surface in some regions. But the distribution was uneven. Some areas had far more ice than others. Some craters showed evidence of ice exposed directly on their floors, presumably excavated by recent impacts. The water was not uniformly mixed into the crust. It was layered, concentrated, dynamic. It told a story of a world where water had not simply frozen in place 4 billion years ago and stayed put. Water on Ceres had moved. It had migrated. It had been redistributed by processes that required energy, heat, and time. The third surprise was organic molecules. Dawn's visible and infrared mapping spectrometer detected aliphatic organics concentrated near Ernetek crater in Ceres's northern hemisphere. These were not the simple, single-carbon molecules that form easily in the harsh radiation environment of space. They were longer-chain hydrocarbons, the kind of molecules associated on Earth with biological processes or with specific geological reactions involving liquid water. Their presence on Ceres was not proof of life, but it was proof of chemistry that was far more complex than anyone had predicted for a world this small and this cold. The picture that emerged from Dawn's data was revolutionary. Ceres was not a dead rock. It was not a fossil. It was not a museum piece preserved in amber since the birth of the solar system. It was geologically active, chemically complex, water-rich, and almost certainly harboring liquid brine beneath its surface at this very moment. 2 centuries of assumptions, 2 centuries of textbook entries, 2 centuries of treating Ceres as the most boring object in its neighborhood had been spectacularly, comprehensively wrong. But here is the problem. None of this should be possible, according to the physics of how small, cold bodies evolve over billions of years. And that contradiction, that impossible gap between what the models predict and what the spacecraft observed, is where the real story begins. The core problem with Ceres can be stated in a single sentence, and that simplicity is what makes it so deeply unsettling. Ceres should be dead, and it is not. Every thermal model, every calculation of heat loss, every simulation of how a body this size and this composition should evolve over 4.5 billion years arrives at the same unequivocal conclusion. The interior of Ceres should have cooled below the freezing point of any plausible liquid long ago. Any ocean it once possessed should be solid ice, locked in a permanent, rigid, unchanging state. Any geological activity should have ceased billions of years before the first dinosaurs walked on Earth, before the first animals crawled out of the oceans, before complex life of any kind appeared on our planet. The models are clear, the physics is straightforward, and yet the evidence sent back by Dawn is equally clear. Ceres has been geologically active within the last few million years, and possibly within the last few 100,000 years. Something is keeping this world alive, and nobody can fully explain what it is. To understand why this is so profoundly problematic, you need to understand how planetary bodies lose their heat. And to understand that, start with a simple image. Take a pie out of the oven, set it on the counter. It is hot, steaming, radiating warmth into the kitchen air. If you wait long enough, it will cool to room temperature. The bigger the pie, the longer this takes, because a larger pie stores more heat relative to the surface area through which it can lose that heat. A small tart cools in minutes. A deep dish casserole might stay warm for an hour. The principle is intuitive and universal. It applies to baked goods, to cooling coffee, and to planets. When the solar system formed 4.6 billion years ago, everything was hot. The process of planet formation is not gentle. The protoplanetary disk, the enormous rotating cloud of gas and dust that surrounded the infant sun, was a crucible of violent collisions. Microscopic dust grains collided and stuck together, forming pebbles. Pebbles accumulated into boulders. Boulders smashed into one another to form planetesimals, objects miles across. These planetesimals continued to collide and merge in a chaotic, turbulent cascade that released staggering amounts of kinetic energy, all of which was converted into heat. Every significant body in the early solar system was heated by this bombardment. The larger the body, the more heat it accumulated. Earth, assembled from billions of impacts over tens of millions of years, was so hot when it finished forming that its entire surface was a magma ocean, a globe-spanning sea of molten rock glowing dull red against the darkness of space. But collisions were not the only heat source. The early solar system contained an abundance of short-lived radioactive isotopes, particularly aluminum-26. This isotope is created in supernova explosions and injected into the gas clouds from which new star systems form. Aluminum-26 is fiercely radioactive. It has a half-life of only 717,000 years, meaning that half of any given sample will decay into magnesium-26 within that time, releasing energy in the process. In the first few million years after the solar system's birth, aluminum-26 was so abundant and decaying so rapidly that it generated enough heat to melt the interiors of even relatively small bodies. This is almost certainly what caused Ceres to differentiate, to separate into layers. The heat from aluminum-26 melted the ice and warmed the rock enough for gravity to sort the materials by density. The heavy, rocky material sank to the center, forming a core. The lighter ice and water rose to the outside, forming a mantle and eventually a frozen crust. Differentiation is a one-way process. Once the layers form, they are supposed to stay put forever. But aluminum-26 exhausts itself quickly. Within about 10 million years of the solar system's formation, essentially all of it had decayed away. The furnace was extinguished. From that point forward, a body like Ceres had only two remaining sources of internal heat. The first was residual primordial heat, the warmth left over from formation and from the aluminum-26 era, slowly conducting outward through the body and radiating into space. The second was the decay of long-lived radioactive elements, uranium-238, with a half-life of 4.5 billion years, thorium-232, with a half-life of 14 billion years, and potassium-40, with a half-life of 1.3 billion years. These isotopes decay far more slowly than aluminum-26, producing a gentle, steady trickle of heat over billions of years rather than a burst. For Earth, these long-lived isotopes are more than sufficient to maintain geological activity. Earth is massive. Its diameter is nearly 8,000 miles. Its volume is enormous. Heat generated deep in the interior takes an extraordinarily long time to conduct through thousands of miles of rock and mantle to reach the surface and escape. Earth's core is still over 5,000 degrees Celsius after 4.5 billion years. The planet will remain geologically active for several billion years to come. Earth is, in thermal terms, an enormous well-insulated heat battery that is only slowly discharging. Ceres is nothing like Earth. The difference in scale is not just significant, it is crushing. Earth is roughly 13.5 times wider than Ceres, but width is not the important measure. Volume is. Volume determines how much heat a body can store, and volume scales as the cube of the radius. If you double the radius of a sphere, you increase its volume by a factor of 8. If you triple the radius, the volume increases by a factor of 27. Earth's volume is approximately 2,400 times the volume of Ceres. If Earth is a watermelon, Ceres is a grape, and the grape does not stay warm for very long. Surface area, meanwhile, scales as the square of the radius. This means that as a body gets smaller, its ratio of surface area to volume increases. A small body has proportionally more surface through which to radiate heat, relative to the volume of warm material inside. Ceres's surface area to volume ratio is roughly 13 times that of Earth. In thermal terms, this means Ceres loses heat roughly 13 times faster than Earth, relative to the heat it contains. The math is striking. It means that any heat trapped inside Ceres after the aluminum-26 era would have conducted to the surface and radiated into space within a geologically short period. The standard thermal models predict that Ceres's interior should have cooled below the freezing point of pure water within the first 1 to 2 billion years after formation. That leaves a gap of roughly 3 billion years between when the ocean should have frozen and the present day. 3 billion years. That is longer than the entire history of complex, multicellular life on Earth. That is longer than the time from the first photosynthetic cyanobacteria to the appearance of the first humans. That is an almost incomprehensible gulf of geological time. And the models say the ocean should have been gone for all of that time, every drop frozen, every geological process halted. Ceres should have spent the last 3 billion years as a perfectly preserved, perfectly inert ball of rock and ice, drifting in silence through the asteroid belt. And yet the bright deposits in Okata crater are there, the sodium carbonate is there, the ammonium chloride is there. These minerals require liquid water to form. They cannot be produced by any known dry process. They cannot result from cosmic ray bombardment of surface ice. They need brine, salty liquid water, to percolate through cracks in the crust and deposit its dissolved minerals on the surface as the water evaporates or sublimes away. And the spectral characteristics of these deposits, analyzed by a team led by Maria Cristina de Sanctis and published in Nature Astronomy in 2020, indicate that some of the material is astonishingly young, perhaps a few million years old, perhaps a few 100,000 years old. Perhaps in geological terms the process is still ongoing. Let that sink in. The thermal models say the ocean should have frozen 3 billion years ago. The geological evidence says liquid water reached the surface within the last few 100,000 years. The discrepancy is not a small error. It is not a rounding issue. It is a gap of billions of years between what the physics predicts and what the chemistry demonstrates. Something fundamental is wrong with our understanding of this world, and it gets worse. Ahuna Mons deepens the problem. The mountain's steep slopes, sharp edges, and relatively unbattered surface indicate that it formed within the last 200 million years. In geological time, that is recent. On a world that should have been dead for 3 billion years, the formation of a 3-mile-tall cryovolcanic dome 200 million years ago is like discovering that a corpse has grown a new tooth. It is not supposed to happen. It cannot happen, according to the models. And yet there it stands. Consider what the existence of Ahuna Mons requires. To build a cryovolcanic dome 3 miles tall and 11 miles wide, you need a reservoir of mobile, semi-fluid material beneath the surface. This material must be under sufficient pressure to be forced upward through miles of frozen crust. It must be warm enough, or at least fluid enough, to flow, and the flow must be sustained long enough to pile material 3 miles high. None of this can happen on a world that froze solid billions of years ago. The energy budget is not trivial. Pushing viscous, icy material through a conduit from the interior to the surface against the resistance of overlying crust requires sustained internal pressure. That pressure likely comes from a combination of thermal expansion, density differences between the rising material and the surrounding ice, and possibly gas pressure from volatile compounds like carbon dioxide or methane trapped in the brine. Each of these mechanisms requires warmth. Each requires liquid or at least semi-liquid conditions at depth, and each contradicts the prediction that Ceres' interior is a frozen monolith. The composition of Ahuna Mons provides additional clues. Its surface shows a higher concentration of sodium carbonate than the surrounding terrain, similar to the deposits in Orcator crater. This suggests that the material that built the mountain was briny, that it carried dissolved salts from the interior to the surface. The mountain is, in a sense, a frozen fountain, a geyser that erupted in slow motion over thousands or millions of years, piling its output into a dome rather than spraying it into space. There are other features on Ceres that may represent older, flattened versions of Ahuna Mons. Several broad, low domes have been identified in dawn imagery that could be the eroded remnants of former cryovolcanic mountains that have since relaxed under gravity. If each dome represents a separate episode of cryovolcanism, and if the spacing between episodes is a few 100 million years, then Ceres has experienced roughly 15 to 20 major cryovolcanic events over its lifetime. Each event required internal heat, internal pressure, and mobile material at depth. Together, they paint a picture of a world that has been intermittently but persistently active for essentially its entire existence. And it gets stranger. There is a feature on Ceres that does not fit neatly into any category. A thin transient haze was detected by dawn above Orcator crater. This haze, barely detectable in certain lighting conditions, is consistent with water vapor sublimating from the bright deposits and forming a tenuous, temporary atmosphere above the crater. A similar detection had been reported years earlier, in 2014, by the Herschel Space Observatory, which detected water vapor around Ceres from Earth orbit. The detection was controversial at the time, with some scientists arguing it was an instrument artifact. But the dawn observations lent it credibility. Ceres is outgassing. Water is escaping from its surface into space, slowly but measurably. This means the subsurface reservoir is not merely present, it is actively leaking. Material from the interior is reaching the surface right now. The world is exhaling. This active outgassing has implications for the long-term stability of the subsurface ocean. If water is continuously escaping through the crust and sublimating into space, the ocean is shrinking over time. The rate of loss depends on the rate of outgassing, which is not precisely known, but even a slow leak over billions of years would deplete a significant fraction of the original ocean volume. This means either the ocean was once much larger than it is today, or there are mechanisms that replenish it, possibly through the release of water from hydrated minerals in the crust, as they are slowly heated from below. The system may be in a rough equilibrium, with water escaping at the surface and being released from minerals deeper down, maintaining the ocean at a roughly constant volume despite ongoing losses. The organic molecules near Ernetet crater compound the mystery. But before we get there, the Ahuna Mons problem grows deeper still. In 2016, Michael Sori and colleagues at the University of Arizona published a study that made the implications of this lone mountain even more unsettling. Using computer models of ice behavior under Ceres' gravity and surface conditions, they showed that cryovolcanic domes would gradually flatten over time through a process called viscous relaxation. Ice, even extremely cold ice, is not perfectly rigid. Over long timescales, it flows under its own weight, the way glaciers creep down mountainsides on Earth, but far more slowly. A 3-mile tall dome of icy material on Ceres would, over several 100 million years, slowly spread outward and sink, losing its steep slopes and sharp profile until it became an indistinct, rounded hump barely distinguishable from the surrounding terrain. Sori's models predicted that a cryovolcanic dome on Ceres would become effectively invisible after roughly 200 to 400 million years. The implication cut deep. If Ahuna Mons is the only clearly recognizable cryovolcanic dome on Ceres, it is not because it is the only one that ever formed. It is simply the most recent. Earlier domes have been erased by the slow, patient flow of ice over hundreds of millions of years. Their ghosts may still be detectable in subtle topographic anomalies, low rounded mounds scattered across the surface, but their original shapes are gone. If Ceres has been producing cryovolcanic features at a roughly steady rate, forming one new dome every few 100 million years and then gradually erasing it, then Ahuna Mons is the latest entry in a sequence stretching back billions of years. Sori estimated that Ceres may have produced roughly 10 to 20 significant cryovolcanic features over its lifetime. Each one required internal heat, internal pressure, and mobile material at depth. Together, they paint a picture not of a world that flickered briefly with activity and then died, but of a world that has been intermittently but persistently alive for nearly the entire history of the solar system. The thermal models are not slightly off. They are catastrophically wrong. And the fact that they are wrong about one of the most thoroughly studied small bodies in the solar system, a body that was orbited and mapped at close range by a dedicated spacecraft, should give every planetary scientist pause. Because if the models fail here, where the data is rich and the constraints are tight, how confident can we be in their predictions for the thousands of other icy bodies we have never visited? Now, the organic molecules. Aliphatic organics detected near Ernetet crater by Dawn's visible and infrared mapping spectrometer add a dimension to the Ceres mystery that goes beyond geology and into the realm of biology, or at least the precursors of biology. These are not the simple organic molecules, single carbon compounds like methane or formaldehyde, that form readily in space through radiation chemistry acting on icy grain surfaces. These are longer chains of carbon atoms bonded to hydrogen with molecular structures resembling tar, kerogen, or asphalt. On Earth, aliphatic organics of this type are most commonly associated with biological activity. They are found in petroleum, in coal, in the organic-rich sediments of ancient lake beds. They can also form through abiotic geological processes, but those processes typically require liquid water, heat, and catalytic mineral surfaces. The detection was made in 2017 by a team led by Maria Cristina de Sanctis. The organics were found in a patch, roughly 400 square miles in area, concentrated around Ernetet crater. The concentration was significantly higher than what would be expected if the organics had been delivered by meteorite impacts because impacts tend to disperse material widely across the surface and also destroy a significant fraction of the organic molecules through the extreme heat of collision. The localized concentration suggested instead that the organics formed in place on Ceres through reactions occurring at or beneath the surface. If the organics are indeed indigenous, their formation requires conditions that the thermal models say should not exist. Liquid water in contact with mineral surfaces at temperatures warm enough for chemical reactions to proceed. This is not just a geological problem anymore, it is a prebiotic chemistry problem. On Earth, the combination of liquid water, organic molecules, mineral catalysts, and chemical energy is the exact recipe that many scientists believe led to the origin of life approximately 4 billion years ago. Nobody is claiming that life exists on Ceres, not yet, but the fact that all the prerequisites for life appear to be present on a world that was dismissed as dead rubble for 2 centuries is either a remarkable coincidence or a signal that the conditions for prebiotic chemistry are far more widespread in the solar system than anyone assumed. A follow-up study by Ralph Millikan and Jiang Li, published in 2019, used additional spectral analysis to argue that the organic deposits on Ceres were even more abundant than initially estimated. They suggested that the organics might cover up to 45% of the mapped area near Ernetet crater, a concentration that would be extremely difficult to explain through meteorite delivery alone. Their findings strengthened the case for indigenous formation and deepened the puzzle of how a world this cold and this small could sustain the conditions necessary for complex organic chemistry. Several hypotheses have been proposed to bridge the gap between the thermal models and the dawn observations. Each one is plausible in isolation, each one is incomplete on its own, and each one, if ultimately proven correct, carries implications that extend far beyond this one small world orbiting between Mars and Jupiter. The first hypothesis is the antifreeze model. If Ceres' subsurface ocean is not pure water, but a concentrated brine, rich in dissolved salts and possibly mixed with ammonia, then the freezing point could be depressed far below 0 degrees Celsius. Pure water freezes at 0 degrees. A saturated solution of sodium chloride freezes at roughly -21 degrees. A solution of ammonia and water can remain liquid at temperatures as low as -97 degrees Celsius. If Ceres' interior ocean is a thick, briny, ammonia-laden slurry, it could persist as a liquid far longer than a pure water ocean. The evidence supports high salinity. The sodium carbonate and ammonium chloride deposits in Ernetet crater are exactly the minerals you would expect if a dense brine had reached the surface. The presence of ammonia-bearing minerals elsewhere on the surface is consistent with an ammonia-rich interior. But even with the most generous antifreeze assumptions, the thermal models still predict complete freezing by roughly 2 to 2.5 billion years ago. The antifreeze hypothesis buys time, perhaps a billion years of extra liquid. But it does not buy enough. The second hypothesis involves a thermal blanket. Ceres' outer crust is not pure ice. It is a mixture of ice, rock, hydrated minerals, and possibly clathrate hydrates, structures in which gas molecules like methane or carbon dioxide are trapped inside cages of water ice molecules. Clathrate hydrates are excellent thermal insulators. They conduct heat far less efficiently than pure ice. If Ceres' crust contains a significant proportion of clathrate hydrates, it could act as a blanket, dramatically slowing the rate at which heat escapes from the interior. In 2020, Julie Castillo-Roguez and her colleagues at NASA's Jet Propulsion Laboratory published a model incorporating this effect. They showed that a combination of high salinity, moderate ammonia content, residual radioactive heating, and a clathrate-rich insulating crust could, in theory, maintain a thin layer of liquid brine between the rocky core and the icy mantle, possibly extending from about 25 miles beneath the surface to a depth of about 60 miles. The model was internally consistent and matched the dawn observations reasonably well, but it required a very specific set of conditions. The salt concentration had to fall within a narrow range. The ammonia content had to be just right. The proportion of clathrate hydrates in the crust had to be substantial but not so large as to create other compositional inconsistencies. The model worked, but it worked on a razor's edge. Small changes to any single parameter could tip the result from liquid to solid, and several members of the planetary science community pointed out that a model requiring this many fine-tuned parameters might be masking a deeper ignorance. When you need 5 separate factors to all be precisely calibrated to get the right answer, the uncomfortable possibility is that you are missing the one factor that actually matters. A third hypothesis, less widely discussed but gaining attention, involves impact-driven heating. When a large object strikes Ceres, the kinetic energy of the impact is converted into heat. A major impact can heat the subsurface to significant depths, melting ice and creating temporary pockets of liquid water that persist for thousands or even millions of years before refreezing. A crater at 60 miles wide was formed by an impact energetic enough to fracture the crust to depths of tens of miles and potentially to melt or mobilize any ice or brine beneath the impact site. Some researchers have proposed that the bright deposits in Occator are not evidence of a pre-existing global ocean at all, but rather the result of impact-generated meltwater that formed locally and briefly during and after the crater-forming event. This hypothesis is attractive in some ways because it does not require a continuously liquid ocean. Each major impact would create its own temporary reservoir of meltwater, which would then slowly refreeze over millions of years, leaving behind salt deposits as it did so. But it has significant problems. The spectral youth of the deposits in Occator, estimated at a few 100,000 years, is far younger than the crater itself, which is 34 million years old. If the brine was created by the impact, it should have refrozen within a few million years at most. The fact that fresh deposits exist 30 million years after the impact event suggests that something other than impact heating is sustaining the liquid. Moreover, the impact hypothesis does not explain Ahuna Mons, which is located far from any major impact crater. If cryovolcanism on Ceres were purely impact-driven, you would expect cryovolcanic features to be concentrated inside or near large craters. Ahuna Mons stands alone on a relatively unremarkable plain, with no obvious external trigger for its formation. Its existence requires an internal mechanism, a source of heat and pressure originating from within Ceres itself, independent of impacts. The debate continues. The thermal evolution of Ceres remains one of the most active areas of research in planetary science. Each new analysis, each reprocessing of dawn data, each new laboratory experiment simulating conditions inside small icy bodies adds a piece to the puzzle. But the puzzle is far from complete. What we know for certain is that the standard thermal evolution models underpredict the geological activity of Ceres by a staggering margin. What we do not know is why. And that gap between what we know and what we do not know is where the most important discoveries in planetary science may be hiding. But it required a very specific set of conditions. The salt concentration had to fall within a narrow range. The ammonia content had to be just right. The proportion of clathrate hydrates in the crust had to be substantial, but not so large as to create other inconsistencies. The model worked, but it worked on a razor's edge. Small changes to any parameter tipped the result from liquid to solid, and several members of the scientific community pointed out that a model requiring this many fine-tuned parameters might be masking a deeper ignorance. When you need 5 separate factors to all be precisely calibrated to get the right answer, the uncomfortable possibility is that you are missing the one factor that actually matters. Something is wrong with our assumptions. That phrase, or variants of it, appeared in multiple published papers and conference presentations in the years following Dawn's discoveries. Not wrong in the sense of completely incorrect, but wrong in the sense that the models are incomplete. There is a missing piece, an unknown heat source, an unaccounted for chemical process, a mechanism that generates energy in ways the standard models do not include. One candidate for the missing mechanism is serpentinization. This is a real geological process that occurs on Earth, right now, deep beneath the ocean floor. When iron-rich and magnesium-rich minerals in the Earth's mantle come into contact with liquid water, they undergo a chemical reaction that transforms them into a class of minerals called serpentines. The reaction is exothermic, meaning it releases heat, and it releases a significant amount of it. Serpentinization also produces hydrogen gas as a byproduct, which is significant for entirely different reasons. Hydrogen gas is an energy source that certain microorganisms on Earth use to fuel their metabolism. Some of the deepest, most isolated ecosystems on our planet, microbial communities living in cracks in rock miles beneath the surface, are powered not by sunlight, but by the chemical energy released through serpentinization. If serpentinization is occurring inside Ceres, where liquid water percolates through cracks in the rocky core and reacts with iron-rich silicate minerals, it could provide a slow, steady trickle of heat that the standard thermal models do not include. The reaction rate would be slow, limited by the rate at which water and rock come into contact. But on a timescale of billions of years, even a slow reaction rate could generate meaningful amounts of heat. Some researchers, including those working with data from the Dawn mission, have suggested that serpentinization could be the critical missing factor that explains how Ceres maintains a liquid layer despite the predictions of traditional thermal models. But the case for serpentinization as the sole solution is not airtight. The amount of heat generated depends on the volume of reactive rock in contact with water, the rate of the reaction, and the availability of fresh mineral surfaces. Once the rock near the core mantle boundary has been fully serpentinized, the reaction stops. New rock must be exposed, which requires fracturing or some other process that creates fresh surfaces. Whether this renewal process could sustain itself for 4.5 billion years on a body the size of Ceres is an open and actively debated question. There is yet another possibility, one that is less often discussed, but potentially more profound. What if the answer is not a single missing heat source, but a combination of factors that, individually, are each insufficient but together cross the threshold? The antifreeze effect of dissolved salts and ammonia lowers the freezing point. The insulating blanket of clathrate hydrates slows heat loss. Residual radioactive decay provides a modest but persistent energy input. Serpentinization adds a chemical heat source. Each factor alone falls short, but stacked together, they might create conditions in which a thin, briny, muddy layer of liquid can persist indefinitely at the boundary between the rocky core and the icy mantle. This synergistic model is, in fact, what Castillo-Roguez and her collaborators proposed. It is the model that best fits the Dawn data, and it is the model that most troubles the traditional approach to planetary thermal evolution, because it suggests that habitability is not a binary property, not a switch that is either on or off, but a continuum that depends on the complex interplay of dozens of factors, many of which we have historically ignored or underestimated. To make this more concrete, consider the specific conditions at Ocata Crater, the site of the brightest deposits on Ceres. The crater is about 60 miles wide, formed by an impact roughly 34 million years ago. When a large object struck Ceres and excavated this basin, it did more than just blast rock and ice into space. It fractured the crust for miles beneath the impact site, creating a network of cracks and channels connecting the surface to the deep interior. If a liquid brine reservoir existed beneath the surface, the impact fractures would have provided pathways for that brine to rise. And the geological evidence suggests that this is exactly what happened. The central bright deposit in Ocata, called Cerealia Facula, sits on top of a dome of material that appears to have welled up from below. The dome rises several hundred feet above the crater floor and is composed of sodium carbonate mixed with hydrohalite, a hydrated form of salt. The composition is consistent with a brine that originated deep beneath the surface, rose through impact-generated fractures, and deposited its dissolved minerals as it reached the surface and lost its water to the vacuum. The outlying deposits, called Vinalia Faculae, are thinner and more diffuse, as though brine seeped outward along near-surface fracture networks and left salt deposits over a wider area. The timing of the deposits is constrained by several independent lines of evidence. The spectral properties of the sodium carbonate indicate that it has not been significantly darkened by cosmic ray bombardment or mixed with surrounding darker material, both processes that would occur over tens of millions of years if the deposits were ancient. The morphology of Cerealia Facula, with its steep-sided dome and well-defined boundaries, also suggests geological youth, and the presence of hydrohalite, which is unstable over long timescales in the vacuum and radiation environment of Ceres' surface, puts an upper limit on the age of the deposits. Taken together, these constraints suggest that briny water was reaching the surface of Ocata crater within the last few million years, and possibly within the last few 100,000 years. This is not ancient history. This is not a relic from Ceres' formation. This is practically happening now, and the inescapable conclusion is that somewhere beneath the surface of Ceres, a reservoir of liquid brine exists today, or existed so recently that the distinction is meaningless. The depth of this reservoir is constrained by gravity data. Dawn mapped Ceres' gravitational field with extraordinary precision, measuring tiny variations in the spacecraft's orbital speed as it passed over different regions of the surface. Beneath Ocata crater, the gravity data reveals a mass deficit, a region where the density is lower than expected. This is consistent with a subsurface reservoir of liquid brine or partially frozen slurry located roughly 25 to 40 miles beneath the surface. The reservoir may extend over an area hundreds of miles wide, containing a volume of liquid comparable to a small sea on Earth, and Ocata is probably not unique. Other craters on Ceres show evidence of bright deposits, though none as dramatic as Ocata's. Halani crater, Oxo crater, and Kupalo crater all display bright patches that may represent smaller-scale brine eruptions. If impacts can tap into subsurface brine reservoirs, and if those reservoirs are widespread rather than localized, then Ceres may be permeated with pockets of liquid beneath its crust, a world that is dry and frozen on the surface but wet and active underneath. There is a parallel here to Earth that is worth considering. On our planet, the deepest known life exists not on the surface, but miles beneath it, in cracks and pores in rock, sustained by chemical energy from water-rock reactions and shielded from the harsh conditions of the surface by miles of insulating material. These deep biospheres are invisible from above. You could stand on the surface directly above them and have no idea they were there. If life exists on Ceres, it would almost certainly resemble these deep Earth ecosystems, microbial, chemotrophic, living in the dark, sustained by the energy of serpentinization or similar reactions, completely invisible from orbit. This possibility has transformed Ceres from a scientific curiosity into a serious astrobiological target. In 2021, the National Academies of Sciences published its Planetary Science and Astrobiology Decadal Survey, a document that sets priorities for NASA's planetary exploration program for the coming decade. Ceres was identified as a high-priority target for future missions. The report specifically cited the evidence for a subsurface ocean, the presence of organic molecules, and the ongoing geological activity as reasons to return to Ceres with more capable instruments. But the deeper significance of Ceres extends beyond the question of whether this particular world is habitable. The real question, the one that keeps planetary scientists awake at conferences and drives graduate students to spend years analyzing spectra and running simulations, is what Ceres tells us about the universe at large. If a body this small, this cold, this isolated, this thoroughly dismissed by centuries of scientific consensus, can maintain the conditions for liquid water and complex organic chemistry for billions of years, then what about all the other small icy bodies scattered across the cosmos? Consider the scale of what we might be missing. In our solar system alone, there are hundreds of thousands of known objects in the Kuiper Belt, the ring of icy bodies beyond Neptune's orbit. Many are similar in size to Ceres or larger. The dwarf planets Eris, Makemake and Haumea are all larger than Ceres. Pluto, the most famous Kuiper Belt object, is significantly larger. Beyond the Kuiper Belt lies the Oort cloud, a vast spherical shell of icy bodies that may extend to distances of up to 2 light-years from the Sun, nearly halfway to the nearest star. The Oort cloud is estimated to contain trillions of objects, most of them never observed and never catalogued. If even a small fraction of these bodies have maintained subsurface liquid water through the same mechanisms operating on Ceres, then the solar system contains not dozens, but potentially millions of tiny, hidden ocean worlds, each one a possible habitat for microbial life, each one invisible from the outside, each one carrying its secrets in silence through the darkness of space. And our solar system is one of hundreds of billions in the Milky Way galaxy alone. The numbers become vertigo-inducing. The math is striking. The implication is not merely that Ceres is more interesting than anyone thought. The implication is that the universe may be saturated with habitable environments that look, from the outside, like nothing more than frozen, dead, worthless balls of rock and ice. We have been looking for life in the wrong places. We have been looking for it on the surfaces of warm, well-lit worlds, in the habitable zones of bright stars, in the places that look most like Earth. And all along, life may have been thriving in the dark, beneath the surfaces of worlds we never bothered to examine. The implications are staggering, and they begin with a world that nobody thought was worth visiting. The story of how humanity has tried to understand Ceres is not a single narrative. It is a series of chapters, each one beginning with hope, proceeding through painstaking effort, and ending with an answer that was either incomplete, surprising, or both. Each chapter built on the failures and partial successes of the one before it, and each one revealed that Ceres was stranger than the previous generation of scientists had imagined. The first chapter begins not with a spacecraft but with a telescope, and it begins with a question so basic it seems absurd. What is Ceres made of? For nearly 2 centuries after Piazzi's discovery, nobody knew. The object was too small and too far away to reveal its composition through the telescopes available. Astronomers could measure its brightness, track its orbit, and estimate its size, but the surface composition, the internal structure, and the presence or absence of water were entirely unknown. Ceres was a point of light with a name and an orbit, and nothing more. The first serious attempt to determine Ceres's composition came in the 1970s and 80s, when infrared spectroscopy became a standard tool in planetary astronomy. By spreading the light reflected from Ceres's surface into its component wavelengths and looking for characteristic absorption features, astronomers could identify specific minerals and compounds. The results were immediately intriguing. Ceres's spectrum showed strong absorption features at wavelengths associated with hydrated minerals, clays and salts that contain water molecules locked within their crystal structures. This was the first direct evidence that water had played a role in Ceres's history. Not liquid water on the surface, but water that had chemically bonded with rock at some point in the past, implying a warm, wet interior early in the body's life. Thomas McCord, a planetary scientist at the University of Hawaii, was among the first to appreciate the significance of these spectral detections. In a series of papers published through the 1980s and 90s, McCord argued that Ceres was not a simple rocky asteroid, but a differentiated body with a complex internal structure. His models suggested a rocky core surrounded by a thick mantle of ice and hydrated minerals, with a thin, dusty crust on top. He pointed out that Ceres's relatively low density, about 2.17 grams per cubic centimeter, was too low for solid rock and too high for pure ice. The only way to reconcile the density with the spectral data was to assume a mixture of rock and ice, layered by differentiation. McCord was, in essence, describing a miniature ocean world, a body that had once been warm enough for water and rock to separate into distinct layers. His work was prescient, but it was also ahead of its time. In the 1990s, few planetary scientists were interested in the asteroid belt, and McCord's models received less attention than they deserved. But let us return to the ground-based era and examine it more carefully, because the history of observing Ceres from Earth is a masterclass in the limits of remote sensing and the ingenuity of scientists working at the very edge of what their instruments can detect. Before McCord's spectroscopic work, there was a longer and more modest tradition of photometric observation, a simple measurement of how much light Ceres reflects and how that brightness changes over time. Photometric light curves, graphs of brightness plotted against the rotation period, were among the first tools astronomers used to study asteroid surfaces in the mid-20th century. By measuring how a body's brightness varied as it rotated, observers could infer the presence of surface markings, albedo variations, and even crude constraints on the body's shape. For Ceres, the light curve was remarkably flat, unlike many smaller asteroids, which show dramatic brightness variations as their irregular shapes present different cross-sections to the observer. Ceres rotated smoothly, its brightness changing by only a few percent over its 9-hour rotation period. This flatness confirmed what the shape measurements would later verify. Ceres was round. Spherical bodies produce boring light curves, because a sphere presents the same cross-section regardless of viewing angle. But the minor variations that did exist hinted at surface features. Patches of slightly brighter or darker material distributed unevenly across the surface. In the 1960s and early 70s, advances in photoelectric photometry allowed astronomers to measure these subtle brightness variations with much greater precision. Larry Lebowski at the University of Arizona conducted some of the first thermal infrared observations of Ceres, measuring not the reflected sunlight, but the heat radiated by the body itself. These thermal measurements provided an independent estimate of Ceres' size, because the total thermal emission depends on both the temperature and the surface area of the radiating body. By combining thermal measurements with optical brightness data, Lebowski and his colleagues were able to determine Ceres' albedo, the fraction of incoming sunlight that is reflected rather than absorbed. The result was about 0.09, meaning Ceres reflects only 9% of the sunlight that strikes its surface. This makes Ceres quite dark, roughly the brightness of fresh asphalt, and significantly darker than many other objects in the asteroid belt. The low albedo suggested a surface dominated by dark, carbon-rich minerals, a finding that was consistent with the spectroscopic detections of hydrated silicates, and consistent with the idea that Ceres had a composition more similar to carbonaceous chondrite meteorites than to the dry, basaltic material found on Vesta. The thermal observations also revealed something else. The surface of Ceres was remarkably uniform in temperature. As the body rotated, the temperature difference between the subsolar point, the spot where the sun is directly overhead, and the terminator, the line between day and night, was smaller than expected. This thermal inertia, the resistance to temperature change, indicated a surface material that conducted and stored heat moderately well, consistent with a regolith of fine-grained, porous rock mixed with ice or hydrated minerals. So a surface of pure ice would have shown different thermal properties. A surface of bare rock would have shown different properties still. The thermal data pointed toward a complex surface, one that was neither purely rocky nor purely icy, but some intermediate composition, a conclusion that every subsequent observation would confirm and elaborate. The adaptive optics revolution of the 1990s brought a new generation of observations. Adaptive optics systems use deformable mirrors that flex hundreds of times per second to counteract the blurring effects of Earth's atmosphere, effectively sharpening the telescope's vision to near its theoretical diffraction limit. For the first time, ground-based telescopes could compete with space-based observatories for resolving the largest asteroids. In 2001, a team using the Keck-2 telescope in Hawaii obtained adaptive optics images of Ceres that showed a generally round disk with hints of surface features, including what appeared to be a large, dark region in the southern hemisphere. These images were a dramatic improvement over anything previously obtained from the ground, but they still could not resolve features smaller than about 50 miles across. Ceres was revealing itself grudgingly, in hints and suggestions rather than definitive details. The spectroscopic investigations continued to mature as well. In the 2000s, astronomers using larger telescopes and more sensitive spectrometers refined the mineral identifications on Ceres' surface. Andrew Rivkin at the Johns Hopkins Applied Physics Laboratory published several important studies demonstrating that Ceres' near-infrared spectrum was consistent with a mixture of magnesian, carbonates, ammoniated clays, and iron-rich phyllosilicates. The presence of ammoniated minerals was particularly significant because ammonia is an effective antifreeze that lowers the melting point of water ice. If ammonia was present in Ceres' interior, as well as on its surface, it could help explain how liquid water might persist at temperatures well below the normal freezing point. Ammonia is also a volatile that is more commonly associated with the outer solar system, particularly the satellites of the giant planets. Its presence on Ceres suggested that the body had either formed farther from the Sun than its current orbit and migrated inward, or that it had accreted material that originated in the colder regions of the protoplanetary disk. Either way, ammonia on Ceres was a clue to the body's origin, and it was a clue that deepened the mystery rather than resolving it. The years immediately preceding Dawn's arrival saw a flurry of preparatory observations designed to optimize the spacecraft's science plan. Ground-based radar observations from the Arecibo Observatory in Puerto Rico and the Goldstone Deep Space Network antenna in California's Mojave Desert bounced radio waves off Ceres and measured the returned echoes. Radar observations can provide information about surface roughness, composition, and the presence of buried ice. The radar results for Ceres were tantalizing but ambiguous. The surface appeared moderately rough at radar wavelengths, and there were hints of subsurface reflectors that could indicate layers of buried ice, but the resolution was too coarse to draw definitive conclusions. Still, the radar data helped the Dawn team plan their observation strategy and identified regions of particular interest for close-up examination. It is worth stepping back at this point to appreciate the cumulative effect of these decades of observations. By the time Dawn arrived at Ceres in March of 2015, the scientific community had assembled a remarkably detailed pre-arrival portrait of the target. They knew it was roughly spherical. They knew it was dark. They knew its density indicated a mixture of rock and ice. They knew its surface contained hydrated minerals, carbonates, and ammoniated clays. They suspected it had once been warm enough for water and rock to separate. They had detected water vapor emanating from its surface, and they had glimpsed a mysterious bright spot in Hubble images that defied easy explanation. What they did not know, what they could not know until a spacecraft entered orbit and began systematic observation, was how all these pieces fit together. They had the edges and corners of the puzzle. The interior was blank. Dawn's job was to fill it in. And this brings us to a more detailed examination of Dawn's instruments, because the quality of the answers a spacecraft can provide depends entirely on the quality of the instruments it carries. And Dawn carried a suite of 3 primary instruments that represented 3 fundamentally different approaches to studying a planetary surface. The framing camera, built by the Max Planck Institute for Solar System Research in Germany, was Dawn's primary imaging instrument. It consisted of 2 identical cameras, a redundant pair designed to protect against hardware failure during the long mission. Each camera used a charge-coupled device detector with a resolution of 1024 by 1024 pixels, and each was equipped with a filter wheel containing 7 narrowband color filters spanning the visible and near-infrared spectrum, plus a clear broadband filter for high signal-to-noise imaging. The framing camera could take images in rapid succession, allowing stereo mapping of the surface topography, and its color filters could distinguish between different surface materials based on their spectral reflectance properties. At the lowest orbit altitude of 230 miles, the framing camera could resolve features as small as 115 feet across, a resolution roughly equivalent to seeing individual buildings from orbit. Every image of Ceres that appeared in news stories and scientific publications, every picture of the bright spots in Okata Crater, every photograph of Ahuna Mons rising from the plains was taken by the framing camera. The visible and infrared spectrometer, known as VR, was built by the Italian National Institute for Astrophysics and the Italian Space Agency. VIV operated in 2 channels, a visible channel spanning wavelengths from 0.25 to 1 micrometer, and an infrared channel spanning 1 to 5 micrometers. This wavelength range was chosen specifically to capture the diagnostic absorption features of the minerals and compounds expected on Ceres' surface, including water ice, hydroxyl-bearing silicates, carbonates, organic compounds, and ammonium salts. VR was a mapping spectrometer, meaning that rather than taking spectra of individual points, it built up spectral maps as the spacecraft moved along its orbit, recording the spectrum of every spot on the surface it passed over. The result was a 3-dimensional data cube, 2 spatial dimensions and 1 spectral dimension, allowing scientists to create maps showing the distribution of specific minerals across the entire surface of Ceres. It was VR that identified the sodium carbonate in Okata Crater's bright deposits, It was VIA that detected the organic molecules near Ernutec crater, and it was VIA that mapped the global distribution of ammoniated clays, confirming and extending the ground-based spectroscopic detections. The gamma-ray and neutron detector, known as GRAND, was built at Los Alamos National Laboratory. GRAND operated on an entirely different principle from the cameras and spectrometers. Instead of measuring reflected or emitted light, GRAND detected subatomic particles. When cosmic rays, high-energy protons and heavier nuclei that permeate interplanetary space strike the surface of an airless body, they interact with the atoms in the surface material and produce cascades of secondary particles, including gamma rays and neutrons. The energies and fluxes of these secondary particles depend on the elemental composition of the surface material. By measuring the gamma rays and neutrons escaping from Ceres' surface, GRAND could determine the abundances of specific elements, including hydrogen, iron, potassium, thorium, and silicon, to a depth of about 1 meter. The hydrogen measurements were particularly important because hydrogen is a proxy for water. Wherever GRAND detected high hydrogen concentrations, scientists could infer the presence of water ice or hydrated minerals in the near-surface material. The GRAND data revealed that Ceres' surface is remarkably rich in hydrogen, with concentrations increasing toward the poles, consistent with the presence of near-surface ice that is more stable against sublimation at high latitudes where temperatures are lower. Together, these three instruments provided a comprehensive view of Ceres that no single instrument could have achieved alone. The framing camera revealed the surface morphology, the shapes and sizes of craters, mountains, fractures, and flows. VIA revealed the surface composition, the identity and distribution of minerals and organic compounds, and GRAND revealed the elemental composition of the near-surface material, the abundances of the atoms that make up those minerals. It was the synthesis of all three data types that allowed the Dawn team to construct the detailed geological and geochemical models of Ceres that now inform our understanding of this world. But the instruments had limitations, and those limitations define the boundaries of our knowledge and the questions that remain unanswered. The framing camera could see the surface, but not beneath it. VIA could identify minerals on the surface, but could not determine whether those minerals extended to depth, or were merely a thin veneer. GRAND could probe to a depth of about 1 meter, but the subsurface ocean, if it exists, lies tens of miles below the surface, far beyond the reach of any instrument Dawn carried. None of Dawn's instruments was designed to search for life. None could detect biological molecules. None could distinguish between organic compounds produced by geological processes and organic compounds produced by biology. Dawn was a geological mission, not an astrobiological one, and the questions it raised about life on Ceres were not questions it was equipped to answer. The decision about what instruments to include on a spacecraft is always a compromise between scientific ambition and practical constraints. Mass, power, telemetry bandwidth, and cost all impose limits on what can be carried. Dawn's total instrument payload massed about 45 kilograms, a fraction of the spacecraft's total mass. Every additional instrument adds mass, and in space, mass is money. Each kilogram requires more fuel, more powerful launch vehicles, and more complex engineering. The instruments that were selected for Dawn were the instruments judged to provide the highest scientific return per kilogram, per dollar, and per watt of power. Life detection instruments, which tend to be complex, power-hungry, and massive, were never seriously considered for Dawn, because the mission was designed before anyone suspected that Ceres might be a habitable world. This is the cruel paradox of planetary exploration. You cannot know what instruments you need until you have been there, but you cannot go there without choosing your instruments years in advance, based on your best predictions of what you will find. Dawn's instruments were chosen based on the assumption that Ceres was a geologically dead body whose primary scientific interest lay in its status as a relic of the early solar system. The discovery that Ceres is geologically active and potentially habitable came after the mission was designed, built, launched, and already orbiting its target. By then, it was too late to add a mass spectrometer or a life detection instrument. Dawn could only observe with the tools it had and hoped that the next mission would carry the instruments needed to answer the questions it raised. The second chapter belongs to the Hubble Space Telescope, and it represents one of the most frustrating near misses in the history of planetary observation. In 2003 and 2004, a team led by Joel Parker and colleagues used Hubble's advanced camera for surveys to capture the highest resolution images of Ceres ever obtained from Earth orbit. The images showed a roughly spherical body with a mottled surface of dark and light patches. One bright spot in particular, located in the northern hemisphere, caught the attention of the team. It was brighter than anything else on the surface, and it remained visible in multiple images taken at different times, ruling out a transient phenomenon like an asteroid collision. The team speculated that it might be a large impact crater filled with fresh ice, or possibly a region of exposed salt deposits. But Hubble, for all its power, could only resolve features larger than about 20 miles across on Ceres' surface. The bright spot was tantalizing, but unresolvable. It hinted at something unusual without revealing what it was. Years later, when dawn arrived and mapped Occultata crater in extraordinary detail, it became clear that what Hubble had glimpsed was the same complex of bright deposits that would rewrite the story of Ceres, if only the resolution had been higher. If only the spectral instruments had been more sensitive. The discovery of Ceres' activity might have come a decade earlier. The Hubble observations did contribute one critical measurement. By tracking the precise shape of Ceres as it rotated, the team was able to confirm that the body was an oblate spheroid, slightly flattened at the poles, consistent with a body that had achieved hydrostatic equilibrium under its own gravity. This shape is significant because it is one of the criteria used by the International Astronomical Union to distinguish dwarf planets from irregular asteroids. A body in hydrostatic equilibrium has enough mass for gravity to have overcome the structural strength of its material and pulled it into the most energy-efficient shape, a sphere. Ceres met this criterion unambiguously. It was a world, not a rock. And in 2006, when the IAU established the formal category of dwarf planet, Ceres was classified accordingly. But the promotion came quietly. The headlines that year were all about Pluto's demotion. Ceres' elevation was a footnote in a controversy that had nothing to do with it. The third chapter belongs to the Herschel Space Observatory, a European Space Agency telescope that operated from 2009 to 2013. In an orbit around the Sun at the second Lagrangian point, about 1 million miles from Earth, Herschel was designed primarily for infrared and submillimeter astronomy, specializing in the detection of cold gas and dust in the universe. But in 2014, a team led by Michael Kuppers published a result in the journal Nature that sent shockwaves through the planetary science community. Kuppers and his colleagues had used Herschel to look for signs of water vapor around Ceres. The detection was made using Herschel's heterodyne instrument for the far infrared, an exquisitely sensitive spectrometer capable of detecting faint emission lines from specific molecules. And the instrument found something remarkable, a clear spectral signature of water vapor emanating from Ceres. The signal was faint, corresponding to a production rate of roughly 6 kilograms of water per second, but it was unmistakable. Ceres was outgassing. Water molecules were escaping from its surface into space. The detection was controversial. Some researchers questioned whether the signal might be an instrument artifact or a contamination from some other source. The amount of water vapor detected was tiny, at the very edge of Herschel's sensitivity, and the signal appeared to vary with Ceres' position in its orbits, being stronger when Ceres was closer to the Sun and weaker when it was farther away. This variability was consistent with sublimation, the direct conversion of surface ice to vapor driven by solar heating. But it was also consistent with other explanations, including cryovolcanic venting from the interior. The Herschel detection was never definitively confirmed by an independent observatory before the telescope was decommissioned. But it planted a seed. For the first time, there was direct observational evidence that Ceres was not entirely dead. Something was happening on or near the surface that was releasing water into space. And that something, whatever it was exactly the kind of activity that a thoroughly frozen, geologically inert body should not be capable of. The fourth chapter is the longest and the most dramatic. It is the chapter of Dawn, and it is a story not just of discovery, but of perseverance against institutional indifference and bureaucratic obstacles that nearly killed the mission before it left the ground. The Dawn mission was conceived in the late 1990s by Christopher Russell, a space physicist at the University of California, Los Angeles. Russell's vision was bold: use ion propulsion to visit two of the largest objects in the asteroid belt, Vesta and Ceres, and study them as examples of fundamentally different types of early solar system bodies. Vesta, dry and rocky, represented one pathway of planetary evolution. Ceres, wet and icy, represented another. By comparing the two, scientists could learn how the same starting materials, the dust and gas of the protoplanetary disk, could produce radically different outcomes, depending on distance from the Sun, water content, and thermal history. The proposal was selected by NASA in 2001 as a Discovery-class mission, a category reserved for focused, relatively low-cost planetary science missions. But the path from selection to launch was tortuous. Cost overruns, technical problems with the ion propulsion system, and shifting priorities within NASA threatened the mission repeatedly. In 2006, NASA cancelled Dawn entirely, citing budget concerns. The decision provoked an outcry from the planetary science community, and after an appeal by the Dawn team and a review by an independent board, the cancellation was reversed. Dawn was reinstated and given a new launch date. It was one of the few times in NASA history that a cancelled mission was brought back from the dead. The near cancellation is worth pausing on, because it illustrates something important about how science works, or fails to work, at the institutional level. Dawn was nearly killed, not because the science was weak, but because the mission was considered unglamorous. Asteroids and dwarf planets did not capture the public imagination the way Mars or the outer planet moons did. There were no stunning ring systems, no dramatic volcanoes, no possibility of finding fossilized bacteria in ancient riverbeds. The asteroid belt was perceived as boring, and boring does not attract funding. Russell and his team had to fight for years to keep the mission alive, arguing against the prejudice that small bodies were not worth visiting. History would vindicate them spectacularly, but in 2006, standing in front of a review board defending a cancelled mission to a world most people had never heard of, vindication was far from certain. Dawn launched on September 27, 2007. Its journey has already been described in this narrative, from the Mars gravity assist to the Vesta orbit to the long cruise to Ceres. But the details of its scientific campaign at Ceres deserve closer examination, because it was the systematic, methodical lowering of Dawn's orbit over the course of more than 3 years that allowed the team to build the comprehensive picture of Ceres that now drives the scientific debate. Dawn's investigation of Ceres proceeded in stages, each one bringing the spacecraft closer to the surface, and each one increasing the resolution and sensitivity of its instruments. The initial approach phase, from January to April of 2015, provided global views of Ceres from distances of tens of thousands of miles. It was during this phase that the bright spots in Ocata crater were first seen, igniting the firestorm of public interest and scientific curiosity. The survey orbit, at an altitude of about 8,600 miles, began in June of 2015 and produced detailed global maps of the surface in visible and infrared light. The high-altitude mapping orbit, at about 900 miles, began in August and provided the first high-resolution gravity measurements, and the low-altitude mapping orbit, at just 230 miles above the surface, began in December of 2015 and continued through 2016, producing the most detailed images, spectra, and gravity maps ever obtained of any body in the asteroid belt. It was during the low-altitude mapping orbit that the most significant discoveries were made. The detailed spectra of Ocata crater's bright deposits revealed sodium carbonate, ammonium chloride, and hydrohalite. The gravity data revealed the subsurface mass anomaly consistent with a brine reservoir. The gamma-ray and neutron spectrometer mapped the distribution of hydrogen, and therefore water, across the surface. and the infrared spectrometer detected the organic molecules near Ernetet crater. Each discovery raised more questions than it answered. Each piece of evidence pointed toward a world that was far more active and far more complex than anyone had anticipated, and each result deepened the central mystery. How can a body this small remain geologically alive for this long? The extended mission phase of Dawn's time at Ceres deserves its own examination, because it was during this phase that some of the most revealing measurements were made. After completing its primary mission in June of 2016, Dawn entered an extended mission that continued until the spacecraft exhausted its hydrazine fuel in late 2018. During the extended mission, the spacecraft performed additional orbital maneuvers, including dipping into an extremely low orbit with an altitude of just 22 miles above the surface, closer than any spacecraft had orbited a body in the asteroid belt before. At this altitude, the framing camera could resolve features as small as 10 feet across, revealing astonishing detail in the geological structures that had been identified from higher orbits. The low-altitude images of Ocata crater were particularly revelatory. The bright deposits that had appeared as smooth, featureless patches from higher orbits now resolved into a complex landscape of fractured salt flats, lobate flow features, and small mounds that resembled terrestrial salt pans formed by the evaporation of briny water. The central bright area, Cerealia Facula, showed a dome-like structure with radial fractures emanating from its center, strongly suggestive of an intrusive process where material had been pushed up from below. Around the edges of the dome, the salt deposits graded into darker material through a zone of mixed terrain, creating a boundary region where the upwelling brine appeared to have spread laterally before freezing and depositing its dissolved minerals. The level of detail was sufficient to constrain models of the emplacement process. Scientists estimated that the brine had ascended through fractures created or reactivated by the impact that formed Ocata crater, reaching the surface at temperatures well below the freezing point of pure water, but above the eutectic point of the sodium carbonate ammonium chloride brine, meaning the fluid was liquid despite being extremely cold by terrestrial standards. The gravity science measurements during the extended mission were equally important. By tracking the tiny accelerations and decelerations of Dawn as it orbited close to Ceres' surface, scientists could map the gravitational field with unprecedented precision, detecting subtle variations caused by differences in the density of material beneath the surface. The gravity data revealed a mass anomaly beneath Ocata crater, a region where the material is slightly less dense than the surrounding crust. The most natural explanation for this anomaly is a reservoir of brine, salty liquid water mixed with dissolved minerals, sitting in a chamber beneath the crater floor. The gravity data could not directly confirm the presence of liquid, since a porous layer of salt-rich ice could produce a similar anomaly. But combined with the evidence of recent brine eruptions on the surface, the geological youth of the deposits, and the thermal models indicating that impact-generated heat could keep subsurface material warm for millions of years, the gravity anomaly was strongly suggestive of an extant liquid reservoir. The end of Dawn came not with a dramatic failure, but with a quiet exhaustion. The spacecraft's reaction control system used small thrusters fired by the decomposition of hydrazine fuel to maintain the precise orientation needed for scientific observations and communication with Earth. When the hydrazine ran out on November 1st, 2018, Dawn could no longer point its antenna at Earth, and contact was lost. The spacecraft remains in orbit around Ceres today, a permanent but silent satellite of the dwarf planet it revealed. NASA's planetary protection protocols require that Dawn's orbit be stable enough to prevent the spacecraft from impacting Ceres' surface for at least 20 years to avoid contaminating a potentially habitable environment with terrestrial microorganisms. Current models suggest that Dawn's orbit will remain stable for at least 50 years and possibly much longer. In a sense, Dawn has become part of Ceres, an artifact of humanity embedded in the orbital mechanics of a world that humanity barely understood before it arrived. The legacy of Dawn extends beyond its scientific discoveries. The mission demonstrated that ion propulsion could enable the kind of multi-target mission that would be prohibitively expensive with conventional chemical propulsion. It proved that even a modestly funded Discovery-class mission could produce paradigm-shifting science if targeted at the right object with the right instruments, and it established Ceres as a world worthy of further exploration, transforming it from an obscure body known mainly to asteroid specialists into a high-priority target for astrobiology and planetary science. Before dawn, no serious scientist would have proposed a life detection mission to Ceres. After dawn, such proposals are not only conceivable, but actively being studied. The current landscape of proposed Ceres missions reflects the dramatic shift in the body's perceived importance. The 2023 Planetary Science Decadal Survey, the community-driven report that establishes scientific priorities and mission recommendations for NASA, identified ocean worlds as one of the highest priority themes for future exploration, and Ceres was explicitly mentioned as a compelling target within this theme. While the flagship missions recommended in the survey focused on Europa and Enceladus, the report noted that smaller missions to Ceres could be accomplished within the Discovery or New Frontiers cost caps, making them potentially achievable on a shorter timescale than the more expensive outer solar system missions. One particularly creative proposal, studied by a team at the Applied Physics Laboratory, envisions a small fleet of CubeSats deployed into orbit around Ceres by a carrier spacecraft. Each CubeSat would carry a single specialized instrument, and together the fleet would provide comprehensive coverage of the surface and near-surface environment. One CubeSat might carry a radar sounder, another might carry a thermal mapper, a third might carry a high-resolution camera. By distributing the instrument payload across multiple small spacecraft, the mission could achieve a level of scientific return comparable to a single large spacecraft at a fraction of the cost, while also providing redundancy against the loss of any single unit. The CubeSat concept remains speculative, but it represents the kind of innovative thinking that may be necessary to return to Ceres within a reasonable timeframe. Another intriguing possibility involves using Ceres itself as a resource. Several researchers have noted that Ceres' abundant water, ice, and mineral resources make it an attractive candidate for in-situ resource utilization, the practice of using materials found at a destination, rather than bringing everything from Earth. Water can be split into hydrogen and oxygen for rocket fuel. Minerals can be processed for construction materials. The relatively low gravity, about 3% of Earth's, makes launching from Ceres' surface far easier than launching from the Moon or Mars. Some visionary proposals have even suggested Ceres as a future human outpost, a way station for missions deeper into the solar system. These ideas are decades away from realization, if they are ever realized at all, but they underscore the growing recognition that Ceres is not merely an interesting scientific target, but a body with practical significance for humanity's long-term future in space. The fifth and final chapter of exploration, at least so far, is the chapter that has not yet been written. It is the chapter of what comes next, because the Dawn mission, for all its revelations, was not equipped to answer the deepest questions about Ceres. Dawn could observe the surface and measure gravity and detect minerals and map the distribution of elements. But it could not drill beneath the surface. It could not directly sample the subsurface brine. It could not search for biosignatures with instruments designed for that purpose. The most important questions about Ceres, whether the subsurface ocean exists today, what its composition is in detail, whether it contains the chemical energy necessary to support life, and whether life has actually arisen there, remain unanswered. They require a new mission, a return to Ceres with more capable instruments, including perhaps a lander, a drill, and a suite of astrobiology-focused sensors. Several mission concepts have been proposed. One, informally known as Ceres Sample Return, would land on the surface of Ceres, collect samples of the bright deposits in Okata crater, and return them to Earth for analysis in terrestrial laboratories. The advantage of sample return is that Earth-based instruments are far more sensitive and versatile than anything that can be miniaturized for a spacecraft. A returned sample of Cerean salt could be analyzed for trace organics, isotopic ratios, and possible biosignatures, with a level of precision that no remote sensing instrument can match. Another concept, studied by researchers at the Jet Propulsion Laboratory, envisions a lander equipped with a drill capable of penetrating the surface to a depth of several meters. The drill would access subsurface ice and potentially reach a depth where briny liquid might be present. Instruments aboard the lander would analyze the ice and brine for organic molecules, dissolved gases, and chemical signatures of biological activity. A third concept, perhaps the most ambitious, would place an orbiter around Ceres equipped with a radar sounder capable of mapping subsurface structures to depths of tens of miles. Similar radar instruments on Mars orbiters have revealed buried ice deposits and possible subsurface lakes on Mars. A radar sounder at Ceres could directly detect the subsurface brine reservoir inferred from Dawn's gravity data, measuring its depth, extent, and possibly its state, liquid, solid, or somewhere in between. None of these missions has been approved. None has received funding. The planetary science community has identified Ceres as a high-priority target. But turning scientific priority into an actual spacecraft takes time, money, and political will. The earliest a return mission to Ceres could realistically launch is the mid-2030s, more than 20 years after Dawn's arrival. There is a philosophical dimension to the exploration of Ceres that is worth acknowledging, because it illuminates something about the way human beings choose where to look and what to look for. The history of Ceres exploration is, in many ways, a history of institutional bias. For most of the 20th century, planetary science was organized around a hierarchy of prestige. At the top were the planets, Mars, Jupiter, Saturn. Below them the major moons, Europa, Titan, Enceladus. Below those the smaller moons and the rings. And at the bottom, largely ignored, were the small bodies, the asteroids, the comets, the Kuiper Belt objects, the dwarf planets. This hierarchy determined which missions were proposed, which were funded, and which scientists could attract graduate students and build successful careers. A young scientist choosing between studying Mars and studying the asteroid belt was choosing between a well-funded, well-staffed, high-profile field and a poorly funded, sparsely populated, low-profile one. The choice was not difficult, and the result was that the best telescopes, the most advanced instruments, and the most talented researchers were directed away from Ceres and toward more glamorous targets. The consequences of this bias are now visible in the gap between what we know about Ceres and what we know about comparable bodies in the outer solar system. Europa and Enceladus, the two ice moons most commonly discussed as potential habitats for life, have been studied by multiple spacecraft, including the Galileo mission at Jupiter and the Cassini mission at Saturn. Both have dedicated future missions in development. The Europa Clipper, launched in 2024, and the proposed Enceladus Orbilander. Ceres, despite being closer, cheaper to reach, and arguably no less scientifically compelling, has been visited by a single spacecraft that was not designed for astrobiology. The imbalance is striking. And it is a direct consequence of the institutional hierarchy that placed small bodies at the bottom of the priority list for decades. Dawn's discoveries have begun to change this calculus, but the change is slow, and the funding landscape remains tilted toward the outer solar system. The irony is that Ceres may be the most accessible ocean world in the solar system. It orbits in the inner solar system, at a distance that can be reached in a few years, with existing propulsion technology. It has low gravity, making landing and surface operations relatively straightforward. It lacks the punishing radiation environment of Jupiter's magnetosphere, which makes Europa operations so challenging. And its surface deposits of salt and organic molecules provide direct windows into the subsurface environment without requiring a drill or a melt probe to access. If the goal is to search for life beyond Earth, and if the search is constrained by budget and technology, Ceres may offer the best combination of scientific promise and practical accessibility of any target in the solar system. In the meantime, scientists continue to mine the Dawn dataset for new insights. The spacecraft's instruments collected an enormous volume of data during its 3 years at Ceres, and the analysis is ongoing. New papers appear regularly, each one adding a new detail to the portrait of this enigmatic world. But the fundamental questions remain open. Is the ocean still liquid? is serpentinization occurring? Are the organic molecules indigenous or delivered? And the biggest question of all, the one that nobody dares to ask too loudly for fear of being wrong, is there something alive beneath the ice of Ceres? The numbers are striking. A world 587 miles across, containing possibly 200 million cubic kilometers of water, with a rocky core that may be undergoing active chemistry, with organic molecules on its surface, with salt deposits that indicate recent brine eruptions, orbiting quietly in the asteroid belt while humanity spends billions of dollars searching for life on Mars and planning missions to Europa and Enceladus. Ceres has been overlooked before. It was overlooked for 2 centuries after its discovery. The question is whether we will make the same mistake again, or whether this time we will pay attention. There is a question that haunts the study of Ceres, and it is a question that extends far beyond a single dwarf planet in the asteroid belt. The question is this: if we were wrong about Ceres, what else are we wrong about? For decades, the scientific consensus held that Ceres was a geologically dead body, a frozen relic of the early solar system that had long since exhausted its internal heat and settled into permanent quiescence. This consensus was not unreasonable. It was based on well-understood physics, on the thermal models that accurately predict the cooling rates of small bodies, on the observation that objects of Ceres' size should lose their primordial heat within the first billion years of solar system history. The models said Ceres should be frozen, the observations said otherwise, and when models and observations disagree, it is the models that must yield. But the models that failed for Ceres are the same models we use to evaluate every other small body in the solar system. The same thermal calculations that predicted Ceres would be frozen solid by now also predict that most Kuiper Belt objects should be frozen solid. They predict that most of the moons of the outer planets should be geologically inert. They predict that any body smaller than a certain threshold size should have lost its internal heat long ago and should show no signs of present-day geological activity. And for most of these bodies, we have no way to test those predictions. We have never visited them. We have never orbited them with sensitive instruments. We have never looked closely enough to see whether the models are right or wrong. Ceres was the test case. It was the body where we could compare our predictions with direct observation, and the comparison was humbling. The models were wrong. Not slightly wrong, not off by a factor of 2 or 3, but fundamentally wrong about whether the body was alive or dead. If the models failed this test, there is no reason to assume they would pass it for other bodies. The implication is staggering. The solar system may contain far more geologically active, potentially habitable worlds than current estimates suggest, and most of them may be worlds we have dismissed without looking, on the basis of the same thermal models that Ceres has now discredited. Consider the numbers. The asteroid belt alone contains millions of objects, of which several dozen are larger than 100 miles in diameter. The Kuiper Belt, the vast ring of icy bodies beyond Neptune, contains hundreds of thousands of objects larger than 60 miles across and possibly millions of smaller ones. Many of these bodies are composed of the same materials as Ceres: rock, ice, hydrated minerals, organic compounds. Many of them formed under similar conditions and experienced similar early heating from radioactive decay. If the processes that have kept Ceres geologically active, whether they are clathrate insulation, serpentinization, tidal heating from long-gone resonances, or some mechanism we have not yet identified, could operate on Ceres, they could in principle operate on any of these bodies. The question is how many? The most conservative estimates, based on extrapolating from the known property of Ceres and accounting for the different conditions in the outer solar system, suggest that at least a few percent of large Kuiper Belt objects could harbour subsurface liquid water. A few percent of hundreds of thousands is thousands. Thousands of ocean worlds orbiting in the darkness beyond Neptune, too far from the sun to be warmed by its light, too small to be heated by tidal forces from a giant planet, maintained in a liquid state by the same enigmatic processes that keep Ceres alive. The more aggressive estimates, the ones that assume the thermal models are systematically underestimating internal heat production or overestimating heat loss, push the number even higher. Tens of thousands. hundreds of thousands. The solar system may be teeming with hidden oceans, and we would not know because we have never looked. This possibility reshapes the search for life beyond Earth in a fundamental way. The traditional astrobiology paradigm focuses on a handful of high-profile targets: Mars, Europa, Enceladus, and perhaps Titan. These are the worlds with the strongest evidence for past or present liquid water, the worlds with the most compelling arguments for habitability, and the worlds that have attracted the most funding and the most public attention. But the traditional paradigm assumes that habitable environments are rare, that they require specific conditions: proximity to a star, tidal heating from a giant planet, a thick atmosphere, that are found in only a few places. If Ceres is any indication, this assumption may be wrong. Habitable environments may not require any of those conditions. They may arise spontaneously in any sufficiently large body composed of the right materials, given enough time and the right chemistry. And if that is the case, the search for life has been looking in the wrong places, or rather, looking in the right places but ignoring most of them. The chemistry of life, as we understand it, requires four things: liquid water, a source of energy, the right elements, and enough time for complex chemistry to develop. Ceres appears to satisfy all four criteria. It has liquid water in the form of subsurface brine. It has energy in the form of chemical reactions between water and rock, possibly supplemented by residual radioactive heating. It has the right elements, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the 6 elements that make up the building blocks of all known life, and it has time. Ceres formed 4.6 billion years ago, and the evidence suggests that its subsurface ocean has existed for at least hundreds of millions of years, and possibly much longer. 4.6 billion years is more than enough time for life to arise. Life on Earth appeared within the first billion years of the planet's history, and possibly within the first few 100 million years. If the same chemical processes that produced life on Earth can operate in the subsurface ocean of Ceres, there has been ample time for them to do so. But there is an enormous difference between satisfying the known prerequisites for life and actually harboring life. The conditions on Ceres are extreme by any terrestrial standard. The temperature of the subsurface brine, if it exists, is estimated to be well below the freezing point of pure water, sustained in a liquid state only by the presence of dissolved salts and possibly ammonia. The pH may be highly alkaline, similar to the conditions in terrestrial soda lakes or serpentinite springs. The available energy may be sparse, limited to the slow reaction of water with rock in the absence of sunlight. Life in such an environment would need to be extraordinarily slow metabolizing, extraordinarily cold tolerant, and extraordinarily efficient at extracting energy from chemical gradients. No known terrestrial organism lives under conditions identical to those expected in Ceres's interior. But terrestrial biology offers encouraging analogies. Extremophile organisms on Earth have been found in environments that were once considered completely inhospitable to life. Bacteria thrive in the hot, acidic springs of Yellowstone. Archaea metabolize methane in the deep ocean floor sediments at temperatures just above freezing. Microorganisms have been recovered from ice cores, drilled from Antarctic glaciers, where they appear to have survived for hundreds of thousands of years in a state of suspended animation. The deep biosphere, the community of organisms that lives in the rock beneath Earth's surface, extends to depths of several miles and may contain a significant fraction of all life on Earth. These organisms obtain their energy not from sunlight, but from chemical reactions, exactly the kind of energy source that would be available in Ceres's interior. Some of the most relevant terrestrial analogues are found in serpentinite-hosted hydrothermal systems, where the reaction of water with iron-bearing minerals produces hydrogen gas, which is then used as an energy source by methanogenic archaea. If serpentinization is occurring in Ceres's rocky core, as some models suggest, the same energy source could be available to support a subsurface biosphere. The organic molecules detected on Ceres's surface add another dimension to the habitability argument. The aliphatic organic compounds found near Ernatech crater are the kind of molecules that serve as building blocks for more complex biochemistry. They include chains of carbon atoms bonded to hydrogen, the fundamental structural motif of lipids, amino acids, and many other biologically important molecules. The question is where these organics came from. There are three possibilities. First, they could have been delivered to Ceres' surface by impacts of carbonaceous meteorites and comets, which are known to contain a wide variety of organic compounds. Second, they could have been produced on Ceres' surface by photochemical reactions driven by solar radiation or by irradiation from cosmic rays. Third, and most intriguingly, they could have been produced in Ceres' interior by abiotic chemical reactions involving water, rock, and carbon dioxide, the same kinds of reactions that produce organic molecules in terrestrial hydrothermal systems. If the third option is correct, the organics on Ceres' surface are products of the same subsurface chemistry that might, under the right circumstances, give rise to life. Distinguishing between these possibilities is one of the key objectives of any future Ceres mission. The isotopic ratios of the organic molecules, particularly the ratio of carbon-13 to carbon-12 and the ratio of deuterium to hydrogen, can provide clues about their origin. Organic molecules produced by biological processes tend to have different isotopic signatures from those produced by abiotic processes, because enzymes preferentially use lighter isotopes. If the organic molecules on Ceres show an isotopic fractionation consistent with biological processing, it would be powerful, though not conclusive, evidence for life. Measuring these isotopic ratios with sufficient precision requires instruments far more sensitive than anything Dawn carried, another reason why a return mission is urgently needed. There is a broader lesson in the story of Ceres, and it is a lesson about humility. For most of human history, we have assumed that life requires conditions similar to those found on Earth's surface. Moderate temperatures, liquid water in contact with a rocky surface, abundant sunlight, and a protective atmosphere. Each of these assumptions has been challenged and, in many cases, overturned by discoveries on Earth itself. Life does not need moderate temperatures. It thrives at boiling point and near freezing. Life does not need sunlight. It flourishes in the permanent darkness of the deep ocean and the deep subsurface. Life does not need an atmosphere. It exists in hard vacuum in the form of dormant spores that can revive when conditions improve. The only requirement that has survived every challenge is liquid water, and even this may be less restrictive than we once thought, since water can remain liquid at temperatures far below 0 degrees Celsius, when dissolved salts or ammonia depress the freezing point. Ceres challenges us to extend this logic to its ultimate conclusion. If life can exist anywhere that liquid water, chemical energy, and organic molecules are found together, and if these conditions are far more widespread in the solar system than we previously believed, then the universe may be far more biologically rich than the traditional astrobiology paradigm suggests. The search for life beyond Earth has been focused on a few high-profile targets, but those targets may be merely the most visible members of a much larger population of potentially habitable worlds. The true frontier of astrobiology may not be Mars or Europa or Enceladus. It may be the thousands of small, cold, dark worlds scattered throughout the outer solar system, worlds that have been ignored because they do not fit our preconceptions about where life should be found. This brings us to the question of why Ceres matters beyond the scientific community. Documentary narration often concludes with a plea for funding or a call to action, urging the audience to support space exploration or write to their congressional representatives. And there is a practical case to be made along those lines. A Ceres mission would cost a fraction of the Mars program, would answer questions of profound scientific importance, and would demonstrate technologies applicable to future missions throughout the solar system. But the deeper reasons Ceres matters is not practical. It is philosophical. Ceres represents a kind of test for humanity's capacity to pay attention to things that do not demand attention. Mars has volcanoes and canyons and red deserts, and a history that may include ancient rivers. Saturn has rings. Jupiter has storms the size of Earth. These worlds announce themselves. They are spectacular and photogenic and easy to justify to a budget committee. Ceres is none of these things. It is small and dark and featureless to the naked eye, a dot of light that requires a telescope to distinguish from a star. Its surface is the color of mud, Its most dramatic feature is a mountain 3 miles high on a world 500 miles wide, which sounds impressive until you compare it to Olympus Mons on Mars, which is 3 times as high and sits on a world 7 times wider. Ceres does not sell itself. It requires you to look past the surface, literally and figuratively, to see why it is extraordinary, and that is exactly the point. The most important discoveries in science are often made not by looking at the most spectacular objects, but by looking at the most overlooked ones. Penicillin was discovered in a contaminated petri dish. Cosmic microwave background radiation was first detected as an annoying hiss in a radio antenna. The structure of DNA was revealed not by a dramatic experiment, but by careful analysis of X-ray diffraction patterns so subtle that most scientists would have dismissed them as noise. The history of science teaches that the universe hides its deepest secrets in plain sight, in the places where nobody thinks to look. Ceres was hiding in plain sight for 225 years. It was the first asteroid ever discovered, the largest object in the asteroid belt, visible in a modest telescope from any backyard on Earth, and for most of that time, nobody looked at it carefully enough to see what it was. It took a spacecraft armed with 3 instruments and a willingness to spend 11 years traveling through interplanetary space to reveal that this unprepossessing body, this historical footnote, this astronomical afterthought, is a world with a hidden ocean, active geology, organic chemistry, and the conditions necessary for life. If Ceres can surprise us this thoroughly, imagine what the rest of the solar system is hiding. The silence of Ceres is the silence of a world that has been waiting to be heard. Not broadcasting, not erupting, not performing for our benefit, just existing in the cold dark between Mars and Jupiter, doing the slow chemistry that might, in its lightless interior, be producing the most profound phenomenon in the universe. We do not know yet. We cannot know from where we stand. But we know enough to know that the question is worth asking, and we know that the tools to answer it are within our reach if we choose to use them. There is a particular image from the Dawn mission that captures the essence of Ceres better than any description. It was taken during the spacecraft's final approach from a distance of about 29,000 miles. It shows the full disk of Ceres, lit by the distant sun, hanging in the absolute blackness of space. The surface is a mottled grey-brown, pockmarked with craters, unremarkable at first glance. But in the upper right quadrant, there are 2 bright points of light, the ocheta deposits, gleaming like eyes staring back at the camera. They are sodium carbonate, dried brine, the residue of an ocean that may still exist beneath the surface. They are not beautiful in the conventional sense. They are not dramatic or colourful or awe-inspiring in the way that Saturn's rings or Jupiter's bands are awe-inspiring. But they are, in their way, the most remarkable features in the entire solar system, because they are evidence that this small, cold, dark, overlooked world is alive. The connection between Ceres and the broader question of ocean worlds deserves more rigorous examination, because it reveals how a single discovery can cascade through an entire field and reshape assumptions that were so deeply embedded they had become invisible. Before dawn, the phrase ocean world referred to a specific and exclusive category: worlds with global or regional subsurface oceans, maintained in a liquid state by tidal heating from a nearby giant planet. Europa, tidally flexed by Jupiter's enormous gravity, was the archetype. Enceladus, flexed by Saturn, was the confirmatory example. The mechanism was well understood. The gravitational interaction between a moon and its parent planet generates internal friction, which heats the interior and melts ice that would otherwise remain frozen. This mechanism requires 2 things: a sufficiently massive parent planet and an orbital configuration that generates the necessary tidal forces. Without a giant planet, there is no tidal heating. Without tidal heating, there is no ocean, or so the reasoning went. Ceres obliterated this reasoning. It orbits the sun, not a giant planet. It experiences no tidal heating whatsoever. Its interior should be cold and dead by every standard that the tidal heating paradigm would predict. And yet the evidence points overwhelmingly toward geological activity and subsurface liquid. If Ceres can maintain an ocean without tidal heating, then tidal heating is not a prerequisite for ocean worlds. It is one mechanism among several, And if it is one mechanism among several, then the number of potential ocean worlds in their solar systems, and by extension in the galaxy, is far larger than the tidal heating paradigm would suggest. This is not a minor correction. It is a revolution in our understanding of where habitable environments can exist. The tidal heating paradigm restricted ocean worlds to the immediate neighborhoods of giant planets. Remove that restriction, and ocean worlds can exist anywhere in the solar system where there is enough ice and enough heat from any source to maintain liquid water. Radioactive decay alone may be sufficient for bodies above a certain size threshold. Chemical energy from serpentinization may provide an additional contribution. Clathrate insulation may reduce heat loss enough to tip the balance. The specific mechanism matters less than the principle. Small bodies can maintain liquid water for billions of years without any external energy source. The implications for exoplanet science are equally profound. Astronomers searching for habitable exoplanets have traditionally focused on the habitable zone, the band of orbits around a star where surface temperatures permit liquid water. This focus has guided the design of planet-hunting telescopes, the selection of target stars, and the interpretation of transit and radial velocity data. But the habitable zone concept applies only to surface habitability. If subsurface oceans can exist on bodies far from any star, sustained by internal heat and chemical energy, then the habitable zone is not a zone at all. It is a sphere that encompasses the entire planetary system, from the innermost rocky planets to the outermost icy bodies. Every star with a retinue of small, icy bodies is potentially a host to dozens or hundreds of habitable worlds, most of them invisible to our telescopes because they are too small, too cold, and too far from their star to produce detectable signals. The universe may be far more habitable than we have dared to imagine, and Ceres is the evidence that forced this re-evaluation. This line of reasoning extends beyond planetary systems altogether, into one of the most speculative but intellectually compelling frontiers of modern astrophysics: rogue planets. Gravitational interactions during the formation of planetary systems routinely eject planets and smaller bodies into interstellar space, where they drift between the stars without any stellar host. Estimates based on microlensing surveys suggest that rogue planets may outnumber stars in the Milky Way, meaning there could be hundreds of billions of them in our galaxy alone. Most rogue planets are assumed to be frozen, dead worlds drifting in perpetual darkness. But if the Ceres paradigm holds, if internal heat sources like radioactive decay, chemical reactions, and insulating structures can maintain liquid water independently of stellar energy, then some fraction of rogue planets may harbor subsurface oceans. A rogue planet the size of Mars, with a thick ice shell insulating a water mantle heated by long-lived radioisotopes, could in principle maintain liquid water for billions of years, even in the absolute cold of interstellar space. The numbers are extraordinary. Even if only 1 in 10,000 rogue planets has a subsurface ocean, that is tens of millions of hidden ocean worlds in our galaxy alone. Tens of millions of potential habitats for life, drifting silently through the space between stars, invisible to every telescope we have ever built. The connection to the origin of life on Earth is worth noting as well. One of the enduring puzzles in the study of life's origins is where the necessary prebiotic chemistry occurred. The surface of the early Earth was a violent place, bombarded by asteroids and comets, baked by intense ultraviolet radiation, and lacking the protective ozone layer that shields modern life from the harshest solar radiation. Some researchers have argued that the deep subsurface, shielded from these hazards and supplied with chemical energy from water rock reactions, may have been a more hospitable environment for the earliest stages of chemical evolution. If this is correct, then bodies like Ceres, which have maintained deep subsurface environments enriched in water, rock, and organic molecules for billions of years, may represent the most common habitat for prebiotic chemistry in the universe. The surface of a planet in the habitable zone of a star may be the exception rather than the rule. Life may be fundamentally a subsurface phenomenon, one that arose in the dark and only later, on those rare worlds with the right atmospheric conditions, emerged into the light. there is also a practical dimension to the Ceres question that connects to the long-term future of humanity in space. The resource potential of Ceres has been noted by researchers in the emerging field of space resource utilization. Ceres contains more fresh water than Earth. Its water ice, mixed with rock and salt, could be extracted and processed to produce drinking water, breathable oxygen, and rocket propellant. Its surface minerals include clays and carbonates that could be used for construction. Its low gravity, about 3% of Earth's, means that escaping its surface requires a fraction of the energy needed to leave Earth or even the Moon, and its position in the asteroid belt places it within reasonable travel distance of both the inner and outer solar system, making it a potential way station for missions to Jupiter and beyond. Some long-range thinkers have even proposed Ceres as a site for permanent human habitation, a self-sustaining colony that would exploit local resources to support a population in the millions. These visions are speculative and far beyond current technology, but they underscore the point that Ceres is not merely a scientific curiosity. It is a world with practical significance for the future of our species. The cultural significance of Ceres should not be overlooked either. In an era when space exploration competes for public attention with 1,000 other distractions, the story of Ceres offers something rare, a genuine mystery, not a manufactured controversy, not a speculative fantasy, but a real unsolved scientific question with implications that touch the deepest concerns of human existence. Is life a cosmic accident unique to Earth, or is it a natural consequence of chemistry and physics that arises wherever conditions permit? This question has been asked before, but Ceres gives it a new urgency, because if life exists on Ceres, a small dark cold world in the asteroid belt, then it almost certainly exists on thousands of similar worlds throughout the solar system and billions throughout the galaxy. And if that is the case, then we are not alone, and we never have been. The universe is not the empty, sterile void that it appears to be. It is alive, everywhere, and the evidence for this stunning conclusion may be orbiting quietly between Mars and Jupiter, waiting for us to go and look. The contrast between the scientific importance of Ceres and the public attention it receives is one of the great asymmetries in modern science communication. Mars dominates the public conversation about space exploration, as it has for decades. Every Mars rover landing is a global media event. Every press conference announcing a new discovery on Mars generates headlines and social media discussion. Mars has rovers, orbiters, and a public relations apparatus that ensures its continued prominence in the popular imagination. Ceres has none of these things. It has a defunct spacecraft in a slowly decaying orbit, a small community of dedicated scientists working with data collected nearly a decade ago, and no funded mission to carry the investigation forward. The result is that the public narrative of space exploration is shaped not by scientific importance, but by institutional momentum, media accessibility, and the historical accident of which worlds happen to receive the most attention first. This is not to diminish Mars. Mars is a genuinely important target for exploration, and the possibility that it once harbored life is a question worth investigating with the full resources at our disposal. But the disproportionate allocation of attention and funding to Mars, at the expense of other potentially habitable worlds, including Ceres, represents a failure of scientific imagination. We are not searching for life in the solar system. We are searching for life on Mars. And in doing so, we may be missing the very thing we claim to be looking for, because it is hiding in a place we did not think to look. The Dawn mission cost approximately $500 million over its entire lifetime, from initial development through end of operations. This is roughly 1/3 the cost of a single Mars rover mission, and a fraction of the cost of the Europa Clipper or the James Webb Space Telescope. For this modest investment, Dawn transformed our understanding of two worlds and raised questions whose answers could fundamentally alter humanity's view of its place in the universe. The return on investment, measured in scientific knowledge per dollar, is arguably the highest of any planetary mission ever flown, and yet there is no successor, no follow-up, no approved mission to build on Dawn's discoveries and answer the questions it raised. The scientific community has identified Ceres as a compelling target, The technology exists to reach it. The questions are formulated, and the instruments to answer them have been designed. What is lacking is not capability, but will. Let us end where we began, with a world that nobody talks about. Ceres orbits the Sun every 4.6 Earth years, rotating on its axis every 9 hours and 4 minutes, sweeping out its modest ellipse between Mars and Jupiter with the mechanical precision of a clockwork. It has been doing this for 4.6 billion years. For most of that time, it has been alone. No spacecraft, no telescope trained upon it, no intelligence of any kind to notice that it exists. And yet, in its interior, something has been happening. Water has been interacting with rock. Minerals have been dissolving and precipitating. Organic molecules have been forming, breaking apart, and reforming. Salt brines have been migrating upward through cracks and fractures, reaching the surface, freezing, and leaving their white residue on the dark ground. Whether any of this activity has crossed the threshold from chemistry to biology, we do not know. We may not know for decades. But the question hangs in the cold vacuum of the asteroid belt, waiting for us to return and ask it properly. Ceres is the most mysterious world nobody talks about. Perhaps it is time to start talking. There is a fitting irony in the name. Ceres, the Roman goddess of agriculture, of grain, of the harvest that sustains life. Piazzi could not have known, when he chose the name in 1801, that the body he had discovered might actually harbour the conditions for life. He chose the name because Ceres was the patron goddess of Sicily, where he made his discovery, and because naming a celestial body after a goddess seemed appropriate for an object that appeared to be a new planet. But names have a way of becoming prophecies. Ceres the goddess presided over the growth of living things from seeds planted in dark soil. Ceres the world may preside over a similar process, one in which the seeds are organic molecules, and the dark soil is a subsurface ocean heated by the slow chemistry of rock and water. If life exists on Ceres, the name will be the most accidentally perfect act of nomenclature in the history of astronomy. If you have made it this far, you understand why this world deserves more attention than it gets. You understand why the bright spots in Ocata crater are not just geological curiosities, but potential signposts pointing toward one of the most profound discoveries in human history. And you understand why the next mission to Ceres, whenever it comes, may be the most important mission in the history of space exploration. Not because Ceres is the biggest or the most spectacular or the most photogenic world in the solar system, but because it is the one that surprised us. And in science, surprises are where the truth lives. Thank you for watching. Subscribe if you found this interesting. Share it with someone who has never heard of Ceres. And the next time you look up at the night sky and see the familiar constellations, remember that between Mars and Jupiter, too small and too faint to see with the naked eye, there is a world with an ocean, and possibly with life. And it has been there all along, waiting for someone to notice.